Shall we start? Okay. ఇప్పుడు స్టార్ట్ చేస్తున్నాం. ఇది ఇప్పుడు ఓపెన్ డైరెక్ట్ ఓపెన్ కదా, దాంట్లో వెళ్ళి ఓపెన్ చేయాలి. ఇప్పుడు డైరెక్ట్ ఓపెన్ చేయలేము. ఐమాల్ వెళ్ళి అక్కడ ఐ విల్ స్టార్ట్ ఎనీవే. అది good morning all. Let's start the session. So yesterday I just told about the AlphaFold 1 point. I missed it. I told that whatever the sequence already you have in the UniProt will take you to the AlphaFold. That is basically a database. Suppose I have a sequence which even I have not submitted to the UniProt, naturally AlphaFold will not develop a model. So I just want to develop the model and then submit it. Because I have a sequence, if I can directly send it to AlphaFold, then I can directly get the sequence. I can publish along with the structure as well, right? So if that is the case, what you can do is you can go to AlphaFold server. I have given a link here. Just you can type alphafoldserver.com. So AlphaFold server, it's very simple. I'll just show you. We'll not go into the details, but in fact it is very easy also. One thing is you have to register with your academic credentials. Say for example, we have UoH ID. All of you might have your college or official email ID, right? Only they recognize the official email IDs. So otherwise they will consider as a commercial users. So if you register with an academic email ID, then with certain limitation, it is free. Okay. So in the AlphaFold server, I have already registered, so I can see that. Otherwise, you can register. I think within 1 day they will approve it. So you can do multiple things. So I can directly submit the protein sequence, simply the protein sequence here. So I choose protein and I can just paste the sequence here. Then it will develop the model. If it is not available in UniProt, you have sequenced the new protein. You want to develop the structure for that. But the AlphaFold server goes beyond that, because once this was started, they started working on every possible biological structure related problems. So if I have a DNA sequence, I want to develop a structure for that, I can do it. If I have a RNA has a specific secondary structure. So if I have an RNA, then that also can be done. And if you want to do protein-protein interaction, say for example, I have protein A, protein B, and I have only the sequence of these two, but experimentally I know that these two proteins would interact with each other. So now the thing is that I have to develop a model for both the proteins, then I have to develop a model for how these two proteins interact with each other. So that also can be done. Another thing is the protein small molecule interaction. Suppose I have a drug molecule interacting with my protein, but I don't have a structure of my protein. I can only draw on paper that what is that drug molecule. So I can take that protein and the drug molecule to the AlphaFold. It will develop the model for the protein, and then it will find the binding packet of the drug molecule also in that. So protein DNA, protein RNA interactions, DNA, and protein drug interactions, in fact multimeric complexes of the proteins, all this is possible in AlphaFold. However, these are computational predictions. Of course, you have to see, like what we did I told for you about the protein modeling, that you have to see the scores, whether it is reliable or not. So that they themselves give you the scores. Like yesterday we discussed about PLDDT parameter, right? So the parameter you have to check. If it is reliable, then you can go ahead further with that structure. So of course we are keep improving it. So you can choose here what type of things you want to do it. So suppose if I want to do a protein ligand interaction, I can enter the protein here, and then I can add an entity. So here I can say, suppose I have a protein, I know that it forms a dimer, and I have a drug, the drug interacts with the dimer, right? So that means I will give a protein. Of course I can make it 2 copies also, that's fine. Otherwise I can make protein, same sequence again I can paste it here. So suppose there are 2 different proteins interacting, the drug molecule is inhibiting the protein-protein interaction. So I will type the protein 1 here, protein 2 here, and the drug molecule here. Okay, I will show you that how to type a drug molecule. Generally we type it as a Smiles code, which I will show in some databases. Then you just give it, submit the job, it will develop the model. So you have to validate with again PLDDT values whether the developed models are reliable or not. Okay, so there are few other parameters. It will take us more time, but I will share the PPT, and there are links also so that you can go and read about them. What are the parameters you have to look into that? Otherwise, we will get stuck with AlphaFold itself. Okay, all right. So okay, so there are few constraints AlphaFold has. As I said, if you are an academic user, per day you can submit a job up to 5,000 token. What do they mean by a token is one amino acid is a 1 token. I think that is huge enough, right? Suppose if we want to develop a protein which is 500 amino acids which forms a tetramer, still I will be using only 2,000 tokens per day. Of course, it's per day for academic user. So I think it's huge enough. And in other words, we can submit 30 jobs in a day, maximum 5,000 tokens either of the way. So it's not that I will submit small peptides and then multiple times, right? So maximum number of jobs can be 30 jobs, and token is 5,000. Token means one amino acid is one, or one nucleotide is 1 token. If it is a drug molecule, one heavy atom, hydrogens are not counted, one heavy atom is a 1 token. So I think it's a huge enough. Unless otherwise you want to take something around 20-25 big proteins and their complexes, you want to do a complete high throughput, AlphaFold will not allow you as an academic user. Of course, you can pay for it and do that, but academic user, that is the limit. But I generally feel that this is a good enough number to use for any general users from the academic side. Okay, so this is very simple, and only concern I keep insisting in my classes also, that please go through the scores what it has generated, how far you can rely on the structure what it has predicted. As I said, in the same protein, some of the regions would not be predicted with more reliability. Some regions would have been predicted with a very high reliability. So you have to take that call, that can I use this structure to predict the functional capability of that protein. Okay, so that call has to be taken very carefully. So I will move on. Now we will quickly go through Pymol. How many of you have already used any protein visualization tool? Pymol or Chimera or already you have used? Oh, you installed? No. I was just asking in general. Have you used any Pymol, Chimera, or okay, Chimera you have used? Okay, so these Pymol and Chimera are almost equal. Of course, there are slight differences the way they do it. So I will go with the Pymol now. And if you are interested, you can just download Chimera. That is also open source. Pymol is also open source in terms of educational purposes. So you can use either of them. But I will quickly go through the Pymol's one. Sir sent one PDB file yesterday to all of you, right, in WhatsApp. Okay, so that is 1 PW ISE equal, right? That is 1 PW molecule. You can do it in two ways. You can first open Pymol. Suppose if you are not able to find the Pymol, don't worry, just click on the PDB file, it will open it. If Pymol is already installed, it takes a little time. You can skip the activation. If you want to buy Pymol, then you can get the license, then you can activate it. But for educational purpose, you can skip the activation and use it for free. Right, all of you are able to open the file. Okay, so suppose if you have directly opened the Pymol, then you can go to the file, open, open the protein molecule what Sir has already sent you. So it's like simple Word file only, just file open, that's all. One P3W. So if you don't have that protein, you can quickly download from Protein Data Bank. 1 P3W, you can directly type it there. So suppose if you are not having the file, go to RCSB, PDB. In the search tab, you just type this one and you can download it. If you don't have, I will show you quickly. If you go to RCSB PDB, you can say 1P3W. Okay. Here, that's up. And there is an option here, download files. You can download the legacy PDB format. There are different formats, but we will be working on PDB format. So you can go with this PDB file if you don't have that file with you right now. Okay. Shall we go ahead, or all of you have got the protein structure, right? Okay, all right. So in the PDB itself, you can quickly have a basic information about this protein. This protein has 2 chains, and if it has any ligands also would be listed here. And from here, it has some ligand, pyridoxal 5-phosphate. Actually, this is a cofactor in fact. So, and then from here also you can go to UniProt. Okay, so this will take you to the UniProt and it will give you the details about this protein, like yesterday what we discussed. So we are all linked with each other, all the databases. Okay, now what is the use of Pymol and how best we can get the protein information from Pymol? That's what we will do it. So Pymol has, I would say, 4 different windows. One is the comments, where you can choose the comments like your Word file or a PowerPoint file. Another one is a display window. Okay, and these are optional tabs. What are the manipulations we can do on the protein structure? And there is one more at the bottom, which may be not visible properly, but this is a command line. So I will come to the command line. Suppose like people like me are little lazy to search on the tab. Instead, we just directly type the command and do that. So if you want to do very specific jobs, which are routine things, which you don't want to do it again and again for one by one, then you can use the command line. Okay. So now what we have done is we have taken a protein from the PDB, and first thing what we observed in PDB is that this protein has 2 chains, but we are not able to see 2 chains here, right? So if you want to do any manipulation for color, I want to show these 2 proteins as a 2 chains, then I can go to the color option. Okay, before going to that, what I will do is, first thing what I generally advise all of you to do is switching on the sequence. At the right bottom, there is a SEQ option, right? Yeah, you just click on that. It will show the sequence of the whole protein on the top of the window. So this will give you a very big information about your protein, right? All of you got that sequence line there. So you can click on the right bottom. There is a SEQ option. All right. So why is it important? So if you see here, just color everything green as it was. If you see here, it says that there is a chain A at the, please look to the cursor, it says that there is a chain A, and if I keep moving here, I see these are not O zeros, these are oxygens O. Okay, I will come to that little later. And there is a PLP. PLP is, I told you that there is a ligand in your protein, right? So that ligand is PLP. All the ligands, any ligand in your protein would be written with a 3-letter code. Some 3-letter code would have been given by PDB. And then there are oxygens. And I see that there is a chain B. That means there are 2 chains. And again on chain B, so I have the same ligand PLP, and again I have oxygens. And that is the end. So that means that this PDB file, what it actually consists of? It consists of a chain, a protein chain or a polypeptide chain. I can see the length also there, polypeptide chain. Then there is a ligand which is attached to that particular chain, and there are oxygens. These oxygens are basically the water's oxygens. So when you go for X-ray crystallography, as all of us know, it cannot resolve the hydrogen atoms. Right, so water consists of H2O, but you are not able to resolve the hydrogen atom. That means you can resolve only the oxygen atoms. Therefore, only oxygen atoms are there in the list. So those are not zeros. You have to read it as, you can say it as a water molecules, because extracrystallographically you can resolve only oxygen atoms. So therefore, it is a water molecules. So you have a protein chain, ligand, and followed by water molecules. But in my PDB file, I have another protein chain, and the ligand which is attached to that particular chain, and the water molecules which are interacting with that particular chain. So I have 2 chains, but both are very similar. You can call it as a homodimers. Alright? Okay. Now, the thing is that I want to see these in a different colors. So chain A, chain B, I just want to distinguish them. So in this window, if you go to the right side window, you can see that there are 5 options: A, S, H, L, and C. So I will just briefly explain what they can do. These are different options. So this is action, this is show, this is hide, this is label, this is color. Alright. So action means if I want to do any specific action, I can do that. We will do some actions. Of course, all the options we cannot do it now, but we will operate on some actions on that. Show means I want to, how do I want to show my protein? So now we have shown the protein in a cartoon diagram, right? It's literally a cartoon diagram. But I want some of the residues to be shown as a sticks. Say for example, the amino acids which are interacting with my ligand, I want to show them by each atom and the bonds. So how do we do that? We will see. And then hide. I want to hide some part of the protein. I don't want to delete it because I may recall it back, but I want to hide it. So I can use the hide option. And then label. I want to give a labeling on the protein. Say for example, one particular amino acid residue I want to highlight, then I can put a name on that one. So that you can do that. Of course, there are many other options. Color is how do I want to choose the colors. So say for example, right now what we want to do is we want to have two different colors for the chains, right? Because there are two chains. So what you can do is you can go with this option, which I have selected here, and there are multiple options. But if I go by these color options, what will happen is everything would be colored with the same color. I will not be able to distinguish it. Like say for example, suppose if I choose shade of yellow, and there are different shades of yellow, if you choose, the whole system becomes yellow. Right? That is not my idea. What I want to do is I want to color it by chain. If you see, there are options to color it by chain. Within that there are different options which we choose by chain only. So you can create chain bows. That means the chain will start with one color, end with another color. Next chain start with one color. It's like the whole protein will be made into a rainbows. That would be good for school teachers, not for college teachers. So it's better. We have to be more scientifically appealing options, right? So scientifically appealing is generally here the color by each chain. So we can make it color by each chain. Now I am very clear that this is one chain, this is one chain, but which one is chain A, which one is chain B? Just I can see the sequence tab. So the chain A is actually green. For me the chain A is green. If I move down, I can see that there is a cyan, that is chain B. So I know that which is chain A, chain B by just seeing the sequence window. Alright. Okay. So is it clear now? Okay. Now I want to show to the students that this particular protein has alpha helix and beta sheet and there are loops. That means that I have to color it based on its secondary structure. Right? Not by chains, but I want to tell the students that no, this protein has all the three structures. Then I can color it by secondary structure. There is an option by secondary structure. So what I can do is I can give different colors. Even I can make the helix in red, sheets in yellow. If you don't like that combination, I can make the helix in cyan, sheets in pink. So there are three options. Of course, you can operate on that. Now you cannot distinguish the chains, right? But you can distinguish each chain by the secondary structural element what it has. So it's very clear here that this protein has helices. Where are the helices? All the signs are helices, right? Wherever there is a pink or magenta, that is a sheet, beta sheets, and wherever there is a loop, it is shown by light brown. So you can color it by secondary structure as well. Right? Okay, of course we will do coloring and a little more and more as we go further. Right now what we will go with the same window what it is shown here. First we will go to the action window. As I said that I want to see some of the actions what I can do for here. Okay, for instance, if I see my protein, there are always the dots. These are all not dots, the oxygen atoms. Do you remember those oxygen atoms are there? So I want to analyze this protein structure. I may be interested in the water molecules which are buried inside the protein or surrounding the protein. So now I am very clear that these are the water molecules which are inside the protein. These are the molecules which are on the surface of the protein. Okay, I am not interested in water molecules. Basically, let's assume one objective for us that this protein has two chains. Each chain has a same ligand. Right? I want to know what are the residues that are interacting with this ligand and what type of interactions they have. Let us keep that as an objective and go ahead so that we can explore more options in this. Okay, right. So that means that I want to see the protein and ligand, not the water molecules, right? Because water molecules will disturb my view. Of course, we can read in it, but it will disturb my view. So what I can do is I have two options. One is hide the water molecules. So hiding the water molecules, what will happen? Whenever I want, I can recall it back. But now I don't want to hide the water molecules. I am not going to work with water molecules. Therefore, I want to just delete all the water molecules. Okay, so that you can do it in the action window. If you go to the actions, there is an option called remove waters. Sorry, this is add waters. There is an option for remove waters. Okay, so if I click that one, all the water will go. But remember that you cannot recall it. If you want to just hide the water molecules, maybe already I deleted the water molecules, I will show for the ligand. How do you hide it? Suppose you want to hide the ligand, you don't want to see the ligand, you want to see only the protein. Of course, that's what you are doing now. So you can do that one. Okay, right. So the action is, one option is that you want to just delete all the water molecules. Therefore, you can visualize the protein alone. So now it is little clear, right? Where are the secondary structures and other things? Okay. Now we have we are showing this one as a cartoon diagram. I don't want to see it as a cartoon diagram. Rather, I want to see it only the backbones, irrespective of the secondary structure, which is called a ribbon diagram. So in the show option, okay, if you go to the show option, there are many different ways we can see that, but mainly there are two types of views. One is show as, otherwise just a simple list. But both of would have almost same options. If you see here very closely, show as wire, simple show also has a wire. This has a line, this has a line. This has a sphere, this has a sphere. So what is the difference between them? When I use this option, a simple or normal show option, what it will do is, it will not replace this. This structure will be retained. Over and above that, this operation will be done. But once I tell that show as, then what it will do is, it will replace it. Say for an example, suppose if I say show wire, it will show the wires, but the cartoon is not removed. Right? Okay, but I don't want to see it as a wire or the cartoon. I want to see only the ribbon. That is only the backbone. Right? So wire means it will draw each and every atom as a line. So suppose I will just draw a wire for, say for an example, glazing. So I have C alpha, C, O, NH, another C, another hydrogen basically, sorry, alanine, because glazing will not have a side chain. Let's say that this is alanine. Probably glazing is a bad example. Let's say alanine. Okay, so this will show, this is called wire. Alright, cartoon means, you know that, right? So there will be a sheets and helices. This is cartoon. If I go for a ribbon, it will show the whole protein as only the wire. Backbone only it will show. So generally how we draw it. Okay. So, but I don't want to see the cartoon, I don't want to see the wires, I want to see only the ribbons. So in that case, I will ask you to show as lines. Sorry, I said ribbon, right? So now we can see that how the two chains are running over each other. What is the interactions? However, you will not, here you will see the backbone, you will not have any information about the side chains. Right? It shows you a backbone. To some extent it will be helpful. Suppose I want to see how these two chains are interacting with each other, which are the regions are interacting, I will color it by chain. Now I know that which regions are interacting, right? I see that these are the regions interacting, whereas these two are not interacting. Okay, you may ask that, what do you understand? Which residue is interacting? Right? You don't know which residues are interacting. So suppose if you are interested in any specific interaction, you want to see that what are the residues are here on this green. So you can select it on this window. You just click one click, then it will select the residues. And if you go here, you can see here that those residues would have been highlighted here. You see the highlights there, that is the residues what I have selected. So any specific residue, if you want to understand what it is, you can see that. So for example, I want to see whether the other end is a N terminal or C terminal. I can just select it. I will select in green so that it's easy for us right now. So this is the C terminal. This is the C terminal. So that means that the N terminal regions are interacting, the C terminal regions are opposite to each other. That is the C terminal chain A, chain B. That means if one protein is like this, another protein is this way, right? Another one is like this. Suppose you assume that this is N terminal, this is C terminal. So the C terminal is somewhere like this, N terminal is somewhere like this, this N terminal is somewhere like this is somewhere. That is how they interact with each other. To see that, you don't need a cartoon diagram, which will not give you a clear idea, or you don't need a wire diagram, which will not give you a better perception. However, if you do it in the ribbon, it will give you a better perception. So the option is based on what kind of information you want to see from the file. Okay, so that is one of the options in the actions. I will go back to the cartoon, which is most common way of visualizing the molecule. Okay, so next what I told you is that there is no ligand, because the ligand small molecule cannot be shown as a helix or a sheet, right? So obviously there is no ligand. I want to highlight the ligand which is interacting with chain A only. Okay, I repeat, what I want to see, the ligand which is interacting with only chain A. So what I can do is I can go to the chain A. If I see at the end there is a PLP. PLP is my ligand. How do you know? How do I know that it is PLP is my ligand? I told you already in the protein data bank file. If I go little down, you can see everything clearly that this is the protein name and there are two chains which represents the same protein. If some other protein is there, it would have been given in another row. And if you still go down, I will see the information about the small molecules. Here there is a PLP. PLP means pyridoxal 5' phosphate. So this information you can get it from the RCSB PDB file, PDB's data bank. Here I want to see how it interacts with my protein. So what I need to, okay, one thing I forgot to tell you, the right click means selection. The right click, what you do is selection. Okay, right? So if you click, left click is selection, right click if you do, and then pull up or pull down, it will zoom in, zoom out, that's all. So you just hold this, say for example, suppose if I just hold this, okay, it's not working here. So just on the right then you just pull that, okay, that's all. So you can zoom in, zoom out, and of course use the left click, and you can rotate also. So just you rotate the mouse, it will rotate. You can take your own perception, like which way you want to see the protein. Okay, all right. So now we want to see the PLP. So what I have done, I zoom in. Okay, before doing this, we will do one thing. We know that this is a homodimer, right? That means that both are same chains, both will be having the same type of interaction with the ligand. So right now what we will do is, but chain B we will just hide it so that we can focus only on chain A. I'm just hiding the chain A. I'm not hiding deleting the chain B. That means that if I need at later stages, I can recall it. Earlier what I did for water I deleted. Now I cannot recall water, it's gone. Okay, suppose if you want, again you have to download the PDB file, again open it. Okay, but what we will do is, we want to see only chain A. Later on I will see chain B. Therefore what I will do is, I will just hide chain B. So now how do you select? As I told earlier, that you can select one by one, either here, or you can select it here also directly. But it is too long process, as your number of amino acids are so much, you have to keep on dragging it, right? Okay, so by default, the selection for thymol is the amino acid. So if you click, it will select an amino acid. But now what I want to do, I want to select the whole chain, not one simple amino acid, right? So therefore what I will do is, here there is an option, if you notice, residues, atoms, chains and molecules. Alright. So if I choose, it is by default, as I said, it is a residue. But now what I want to do, I want to select the whole chain B, right? So I can change the selection option into chains. Now if I click on any chain, now I click on B side, so it has selected the whole B chain. I can click on A chain, so it selects the whole A chain. It's up to you, because A and B are same homodimer. So if you want to hide A chain, you want to see in the B chain, it's fine. Or you want to hide B and you want to look into the A chain, that is also fine, because since it's a homodimer, it doesn't matter which one you are looking into. So just a general convention that generally we go for chain A to do the analysis. So I'm just selecting chain B. Is this clear, Simon? Chain, because now you don't want to work with residue, I have switched to chains here. Is it clear now? Any doubt about it? No. Okay. Right. What I want to do with this selected chain, I want to just hide the selection. Okay. Now, if you see in the thymol, there are different options. One is all. I can open, let's say, 5 proteins and then compare them. Okay. I think up to 50 proteins you can open the same window and compare them. Okay, but we have opened only one protein, so this is one. So for as all means that only one protein. Right. If you see once you selected, there is an additional one called SCLE. The selection has appeared, right? Did you see this SCLE? That is a selection. So this is the selected one. If you see here, you can see that if I click on that, whether it is selected or unselected. So now what I want to do, I don't want to hide the whole protein. I want to hide only the selected chain, right? Okay, suppose before doing that, I want to name this selection because I may need to recall, right? I may need to recall. If I select something else, this selection will change. So I want to recall it at later point, so that I want to save this selection. What I want to save? Chain B as a separate one. Whatever I do, it will operate only on chain B. I will not disturb chain B. I want to do work only with the chain B. It could be changing the color or completely hiding it or recalling it, whatever, but it has to operate only on chain B, not on chain A. Without whatever we did so far, which happened both on chain A and chain B, right? Now I want to work only with chain B. So this selection means it is chain B, but I want to give some name so that anytime whenever I want, I can recall it. So we will go to the action tab and then give us some name for this one. Say for example, this selection, do it little carefully. I go for the selections action tab, right? Because the selected one, I want to give some name, right? So this is the selection. Here there is an action tab. That means whatever I am going to do, it will operate only on my selection. Say for example, the selected one, I want to change the color to yellow. The selection, I will go for the color. I will change the color to yellow. So it changed only the selection, right? If I go to the whole protein, then everything will be changed to yellow, right? Now the only chain B, I want to give a color. Let's say now blue because already yellow is. Okay, right? But I want to name it because if I select something else, now the selection will shift to that one, right? So I want to select only chain B and then name it. So how to name it? Go to action. There is an option called rename selection, right? Okay, so click on that. It will appear there with the already existing name. Already existing name is SCLE. That is short form for selection, right? We will give some name for this. The simple way of naming it is chain B. Instead of writing chain B, I will write CHB. That means chain B. Okay, of course we can use any other name. It has no restrictions. Only thing is we cannot use space and you have to use only alphanumeric. If you want to have a space, you cannot use a space. Instead, you can use an underscore. Okay, suppose chain B, I want to name it as a chain B as a CH space B. I want to write it as CHB. I can do that, or CH02, let's say chain 2. Okay, I cannot use space. Instead, what I can do is I can use underscore and write chain 2. Right? So I will name it as chain 2 because chain 1, chain 2 is easy to do. Of course, it's up to you how do you want to do it, or if you want to have C capital, that is also fine. So I will make it simple CH underscore 02. Now the name has been changed to CH2. So that means chain 2. Okay, all right. Now I will do it for chain A also, so that whatever the operation I want to do, I can do it only for chain A, only for chain B. Okay, now what I will do, I will select chain A. And now new selection has come. You see, new selection has come. Actually, this is chain A. So I will again rename it as chain 1. Is this clear now? Until now, what we are doing? So basically, we have worked on 2 or 3 options. One is selection. Selection by chain. Of course, we will do it by ligand and other things a little later. One is selection, another one is the color option. So you can change the whole protein's color. I don't want to disturb the yellow color, but blue is not visible. So I want to change the blue to something. What I should do? I have to go to chain 2 because I want to change the color of only the chain 2. That means I will go to only chain 2. Its color I will change to, let's say, magenta, because that is, I think, visible better here. This operation was done only on chain 2. So I can do any operation on the whole protein I can do any operation on only chain 2 or only chain 1 because I have made those selections and I have named it. Alright? Okay. Now, as I said, chain 2 is disturbing us, we will hide it. Right? So, what we can do is, we can go to chain 2. There is an option H. H is for, sorry, I am close. Chain 2 here. Hide everything. That's all. Now chain 2 is hidden. Okay. Now I have analyzed chain A. Assume that I want to recall it. Right? So I can say again go to show now. I want to show it as a cartoon, right? So I can show as a cartoon. So you can play around with hide and show. Okay. Are you clear that it is with respect to only chain 2? So right now what I am doing is chain 2, I am hiding everything. Of course it is in cartoon, so I can just hide the cartoon. Both would operate in the same way. Okay. Now I want chain 1 as a cartoon, chain 2 as ribbon. That is also possible. So now, because these two are now independent, right? In my selection, these two are completely independent. So whatever I do for my selection on chain 2, nothing will happen to chain A. So that way you can do that. Okay, now I will hide chain 2, as I said, like it is disturbing our view, and I will bring the chain 1 to the center of the view, so that I can analyze it very easily, right? Is that clear now? We have almost done at least one operation with each of the options. Action, we did removing water and renaming it, renaming my selection, that we can do it. And suppose you type chain 2 but you don't like now, you want to change it to chain B. For some reason you don't like the name what you have given, again you can rename it, not a problem. Okay, suppose I want to give Prakash 02, Prakash 01. Okay, so you can give it that one, that's not a problem. Right? So anytime you can rename it, whatever the way you want to rename it. Functional groups, yes sir, we can do. What you have to do, I will show you. You label it, that's all right. You can label it so that it will write all the functional groups on the molecule itself. Maybe that also we will do. PLP means ligands functional groups you want to say. Exactly, we will do sir. Labeling maybe we will do it for the ligand. No problem. Okay. Suppose if I forget, you just remind me sir once again, we will do it, it's possible. Okay. So in action, we did removing water and naming of whatever the selection is. In chain, you can label the separate residues also. Show also, we did different way of showing the molecule, cartoon, wire or ribbon, however the way you want. Hide also, we did it now. We selected something and hidden it. Label, we will come to that. Color option also we did. Either you can go by the chain, secondary structure, or irrespective of that, the whole molecule you want to color it or only a selection you color it, you can do that way. Alright. Now our objective is to see what kind of the interaction the ligand has with the protein. Since I have chosen a cartoon, ligand is not shown as a cartoon. So what is the best way of seeing the ligand? Sorry, we are still in the selection mode of chain. So whatever I click, it will select the whole chain. Now I have to go back to the residue option, right? So that it chooses only the residue. So I will go back to the, instead of chain, I will go back to the residue option. So that when I select, it will select only a particular residue. Okay? Because now our objective is to analyze each individual residues interacting with the ligand. Alright? Okay. If you are not able to follow, please stop me. Okay? I feel that I am going fast, but I just rush because we have less time. Okay. Okay, there is a residue here. Now what we planned is actually to see that what this PLP is. So just for our convenience, I will just adjust the view so that the PLP comes to the front plane, so that we can see it was in the back plane. So we are bringing into front plane and more close to the view. So that we can do it by zooming in, zooming out and rotating it. So I have just zoomed in and rotated it so that we can see very clearly, very close by. Okay. So we presume that we are walking into your home. The home is nothing but the protein. So what you have done is you are getting into one particular room rather than looking the home from outside. Right. So the zooming in will give you that, okay, I can see the home from outside. Like this building I can see from outside, but what is in this room? So I have to get into the room, right? So the zoom in will help you to go into that. Okay, so again, once I selected, again you can see that there is a selection. New selection is created. This is temporary. This is completely temporary. Say for example, instead of this, suppose I have selected these two residues now. Now the selection is shifted. So now the selection is for these two residues. So this particular SELE is always temporary. What you select at the current moment of the time, that is kept there. But if you want to make it permanent, you give a name and save it. Okay, right. Okay, now we will go to PLP. Now what we want to see, this is a ligand. So what is the best way of seeing the ligand? There are two ways. One is a stick, so that you can easily understand the groups, or making it into a sphere. So some people like making it into a sphere and coloring it by atom. That is, some people like it. But generally, it's a personal choice. Of course, we can try with the sphere models. Nothing wrong in it. What I would do is, I will go for a sticks. Sticks is easy to understand the structure of the PLP. So now the selection, I can show the selection as sticks. Sorry. Show the selection as sticks. So you see, I will zoom in further. So it has created a stick, right? So one thing is clear here, that there is a phenyl ring. Okay, now it's better the ligand I will give a contrasting color, right? So that I can easily understand that. So already I have kept the selection, that is only for ligand. Maybe I will rename it as ligand _1. That means this ligand belongs to chain 1, right? So while naming it, we just make some logic so that it's easy to understand. So this ligand belongs to chain 1, so I will name it as ligand 1. Of course, it's your choice. You want to write it as PLP1, it's fine. Okay, right. Now what I need to do, I will change the color by element. By element means each atom will be colored in a different way. Say for example, you can color the carbon in gray, nitrogen in blue. That is a convention, right? Oxygen in red. So that without label also you can understand that what are the atoms it is involved. So I will go with, generally what we do is we go with the set 5, which has this option last but second or third. So why I chose this one is, this generally fits into the color convention, general color convention. I think I have selected a wrong one. Okay, yeah. So, of course, it is your choice. If you want to make carbon blue, carbon nitrogen yellow, that also you can do. But generally, I prefer, again, it's a personal choice. But why I do is that when you go for any publication, what they ask is, use the color convention. So in chemistry, there is a convention for colors. It's not that randomly done. Generally, you use black or gray for carbon, white for hydrogen, blue for nitrogen, yellow for sulfur. So this is a convention. So if you publish in any chemistry journal, or which is a computational chemistry, let's say computational biology journal, when you present it, now as a reader, I don't need to see anything. I know that these are carbons, and those red colors are actually the oxygens, and the blue color is the nitrogen. I don't need a label actually, so I can go with it. So that's the basic idea. So how do you do is, go to the action, color, because it's a color, by element. That means each atom will be colored in a different way. I go to the set 5. Okay, in the set 5, I go from the bottom, the third one. From the bottom, it's third one. This color fits with the general chemical convention. Okay, though it is not a rule, but it is easy. Because already our mind is set with that, right? In basic chemistry, it is set with us that this color means this atom. So I can easily read it. Okay. Now, if you are teaching to a student, probably this is first time they know about the color convention. So you want to label it, right? So it's better you label it. How to do that? So the labeling can be done in different ways. Information, like again, I want to label only the ligand, right? I don't want to label the chain and the protein. So what I need to do, I have to go to my ligand. Right? I don't want to see everything is labeled. That will give me a lot of confusion. I am very specific now. I want to see what are the atoms are in my ligand only. So I will not do any operation on my protein or chain 1, chain B. I will go only with my ligand. So I will go to the ligand. There is option L, that is a label. What do you want to label? You want to label the whole ligand name is PLP. So if you want to label it as PLP, that is fine. Generally for publications, we don't go with the atoms, right? We just say that this is the PLP where it sits. So I can label the whole ligand, so that you can use as a residue. Because in convention, one ligand is considered as one residue. So that is how the selection also was done. So you can just label it as a residue. But sir said that I want to know the functional groups, each atom basically. So then I can go for the atom name. I can go for a atom name or element symbol. Atom name means it will write it as oxygen, right? But if it says ON, that is also sufficient for us. So what we will do is we will just write it as an element symbol. So deselect it, then zoom in, you can see that what each one represents. As I said, you can see the clear, sorry, it is not at the center. I think now it's a bit visible. But you can see that these are gray are all carbon, this is nitrogen, red is oxygen, phosphorus is little orange. So this is a general convention. So without label also, once you are used to the chemical convention, you can read it. But when you teach students initially, they will struggle, right? Like they may not be remembering the color codes, basic color codes. So you can just label it and show them that what it is. So that means that this is not it's aromatic because it has that ring, but it is a heterocyclic. It has a nitrogen in it, and it has one phosphate group, and there is one OH group in it. So that is how its structure is looked like. Okay, our idea is a little more than that, right? So now I know what is the ligand in it. And very importantly, what I want to know is that what are the residues around this ligand, right? That is more important for me. Okay, what type of residues are interacting with it? Okay, for that what we can do is you can select the residues which are close by. Okay, so this way you can keep on selecting the residues which are around, right? There is no end for it in principle. So instead of what we will do is, what are the type of, generally it makes a hydrogen bonding, right? So many polar interactions, it could be either polar interaction means either it would be a hydrogen bonding or a charge interaction. Let us see that what are the residues which are making the hydrogen bonding or the charge interactions. Let us see into only those residues, because if you see neighboring residues, all the neighbors will not probably have a hydrogen bonding in it. There could be alanine, there could be isoleucine. They will not make any interaction, right? So let us go very specifically about the interaction, the residues which are making any potential interactions. Okay, so what you can do is, for that you have the ligand, you go to the action, there is an option to find, right? There is an option to find. So go to the action, to find. Remember that what we are doing is the ligand interacting with the others. Okay, the same rule you can apply later, maybe you can try it later. Same rule apply to the chain A, that means C alpha here, it stays there, alright? Okay, then the nitrogen which is connected to the C alpha. I say that it is 0, that means on the wall, 0, 0, Z in -2. So I will keep nitrogen there. So if I give this way for all atoms, will you be able to assemble the whole protein? Each and every atom I will give you XYZ coordinates, right? And you know that which atom will be connected to which atom, because if I say C alpha, obviously it is connected to the nitrogen, and the C beta, and the carbon, not to the oxygen of the carbon, right? That carbon is connected to the oxygen. So you know that where to connect the bonds. Only thing what I need to tell you is that where you will place the balls, right? That is what your PDB file has. Basically, what are the places you can assemble it, but it is projected into a screen rather than assembling into your room. Okay, right? So now if it is given that way, you have to identify the hydrogen bonding, what I should do. Okay, computationally, it's an approximation, but what generally we do is that if there are two polar atoms, because only the polar atoms can make the hydrogen bonds. So if there are two polar atoms, remember that there are no hydrogens here, because it's an X-ray crystallographic structure and it cannot resolve the hydrogens. So there are no hydrogens here basically. Okay. So right. So if there are two polar atoms which are within the distance of 3.5 Armstrong, that means, and the angle is not more than 30 degree, then we presume that they can form the hydrogen bonding. So that is how the hydrogen bonding is defined in the structural biology. I am not talking about the basic definition of the hydrogen bonding. In structural biology, how do you define a hydrogen bond? That is an approximation, I agree, but this is, I would say, the optimum way of defining a hydrogen bonding. So that's why this 3.5, you can see that the cutoff is around 3.5 Armstrong. Sometimes people think that if unless they come close, you don't consider as a hydrogen bonding. Sometimes you relax the cutoff. Let's say even up to 4 Armstrong, we consider that they are coming to them. But the optimum, that's why I said that the optimum distance is 3.5 Armstrong. So, but what we are saying here is any contact means even a non-polar atom which is within 3.5 will be considered as a contact here. If you go for any contact. But what I want to see, only the hydrogen bonding between the protein and the ligand. In that case, I have to go only with the polar contacts, because polar contacts only can make with the hydrogen bonding. So in polar contacts there are many options, but we will say to any atom, because I don't bother whether which atom of the protein involves in that. Only condition I gave is that in the action, I will just repeat it. For the ligand, in the action, I ask you to find the polar contact. In the polar contact action to any atom. Okay, right. So it has created yellow dots. You can see that. That means that these atoms from the protein to ligand can form a hydrogen bonding. All right. Okay. Now, which are those atoms? Which are those atoms? Each needs little amount of. Are you clear about this? Because this is one of the important things you can do it from Pymol. That what kind of interaction your ligand can make with your protein. Okay. In this one, no, it's not considered. Okay. Stringent angle consideration, we don't do it in some cases. I would not say in all cases. It has some reason. One is that you are not able to resolve hydrogen. Basically, you will not see the hydrogen there. Right? That's one thing. Another thing is the system is dynamic. Basically, you have taken a frozen structure. But in reality, the structure is not frozen, right? There will be always a fluctuation. So within that distance, if it is there, you consider it as a hydrogen bonding. Because once, actually, you just imagine how the real system works. You take the protein into water, and the protein keeps fluctuating, right? It's not that all the atoms are frozen completely. So there is always a fluctuation. So that could be a dynamic change which can address for it. So, of course, if you want very specific hydrogen bond, you can define it. However, generally we don't go with the very stringent rule of the hydrogen bond. Like in quantum they do it, but not here actually. Alright, so now let us see that what are those residues which are forming the hydrogen bonding. Now I am clear that which are the residues are involved. So I have to just find out those residues which are involved in this. So I see here that this residue, sorry. So I will write down the residues. What are the residues? There is a alanine, that is 75. So once I select, it shows me that number. So this is alanine 75. That means it must be a backbone. Of course, the side chain cannot form a hydrogen bonding. So alanine 35 is one residue which forms hydrogen bonding. And N155, I will just choose two or three residues only. Of course, you can do the analysis for all the residues which are showing the yellow. Maybe the color also I will change it to red. and T13. So I will just choose these three residues, T13, threonine 13, alanine 75 and alanine 155. Okay, of course there are 5-6 hydrogen bonds because there is a phosphate, so obviously it can form many number of hydrogen bonds. So I am just choosing these three residues and then I will just highlight them. Okay, what are those residues? T13. Here you can see the number. 11 is for serine, alanine is, T13 here. And then A75, A75 and N155. So these three residues I have selected. I will rename it as interaction residues. Just some name so that I don't need to select every time. So I just give it as an interacting residue. And now what I will do is I will make them into a sticks format. That also I will make it as a stick format and I will color it maybe differently from this, maybe in green. So now it's clear that these are the residues which are interacting. Of course, I have not done all the analysis, still 3 more are there. Okay, just I have shown an example. These are the 3 residues which are interacting with my, through hydrogen bonding, which are interacting to my ligand. Okay, now I want to label them. I can do it, right? So I will go to the selection. I have given as interaction residues. Label. Here I will label the residue, right? I don't need to label each individual atoms here. I just want to tell that which are the residues. So I just label the residues. You can see now that it is showing the names of the residues: asparagine, threonine 13 and alanine 75. So you can give the names to that also. Okay, all right. You can keep manipulating with this more and more. Suppose the same way you can choose one chain to, as I said, the chain to chain, because chain A is there. You can add another chain. What is the hydrogen bonding? That will be more in number. And what type of residues you can find out and then label them. And of course, with any kind of analysis you can do it. But what is a very interesting thing in the PyMol is that you can use a command line to do the things beyond this. So there is a, you don't want, say for an example, you want to show this, as I said, as spheres rather than a show as can show as a spheres, which generally I don't prefer, but some people like this way of doing it. This will, but this is interesting one way that it will tell you that how much space the ligand occupies in the active site. So if you are interested not about the atoms but the amount of space it occupies in the active site, you will see. Another way is how big active site, and then in that how well your ligand has set into that, right? So that also you can do. For that what you can do is you can make this is chain A. So chain A you can show as a surface. So this is a very conventional way of seeing the protein ligand interactions, which you might have seen in many publications also, that this is your protein, right, and this is where your ligand looks in. I will do one thing, I will hide the cartoon so that it is very clear. And color I will give only yellow. So you can see here that it's not showing that properly. How it sits into the binding packet, that we can see it clearly. Suppose if you think that this is not sufficient, then what you can do is you can reduce the transparency of your surface to half. That also you can do. So what you do is you go to the display, there are many options, I'm just operating only the settings, transparency. The surface, I can reduce the surface by some 40-50% so that the ligand is highlighted, protein is little dull in color, so that you know that where it exactly it binds. Of course, this number choices, different people use different numbers based on their this thing. So in that, I want to see the secondary structure of the protein also on that. So what I can do is in chain 1, I can ask it to show the cartoon as well, but now cartoon is highlighting so much. What I can do is again reduce the colored transparency of the cartoon also. I can reduce it to, let's say, 50%, so that the cartoon is appearing less, and then you can see the ligand more highlighted. So it's up to how do you want to see. You want to see as a sphere or surface or these things, that you can do it. So it will be useful when you want to talk about any particular protein's function also. Of course, the primal, as I said, that the command line also can be done. Say for example, I want to see that a very simple example I will do it. Now I will just go back to our conventional way, show it as a cartoon, and then the ligand as a maybe spheres, fine. Okay, right. So now what I want to do is, it looks dull because the transparency has been reduced. Okay. I just want to select all the lysines in the protein. For some reason, I just want to see how many number of lysines. Say for example, suppose it is a nucleotide. This is not a DNA binding, but let's say that there is a DNA or RNA binding. What you expect? All the basic residues would be the ones where it would be interacting with the DNA. Because of positive charge, they would be interacting. So you want to show the students that, okay, these are the positive residues. This is where potentially the DNA can come and interact, right? So how do I know that? So there are only two options. One is a lysine and arginine. These are the two. So how do I select? I cannot walk through the sequence and select where K or K or K or. This is very difficult to do that. Instead, that kind of a repeated ones, you can go for the command line. So I'm not going to, there are n number of command lines. So you just type in Google what type of modifications you want to do. Google can, in fact, nowadays Gemini also can suggest you that what exact command you have to use it. So, but I'll just give you an example of command line. Say for example, I want to select only the lysine and arginine residues, because these are the basic residues. Though this protein is not actually DNA binding, let's assume that it is a DNA binding protein. I want to highlight the basic residues. Okay. So the select, that is a common command. Are you able to follow these letters? Okay, I will just type it separately. Select basic residue name K plus R. Okay. I will do one thing. I will just copy this and maybe in Word, what do you call WordPad. So this is the command. So any command any selection can go like this. You first write select, that means select. You give any name. I just give basic residues. If you want to say arginine and lysine or whatever, same rules like underscore can be used or numericals can be used. This is my option. I just write it as a basic residues, comma. This means that residue name, RESN is actually the command. Basically RESN and select are the commands. RESN is the residue name. You are going by the residue name. So you are selecting RESN. Which are the residues? Lysine, you can select only lysine or only arginine, but I want to select both because I want to see all the basic residues. So I say that lysine plus arginine. We can keep on adding other residues also. It has no end. So, but right now I am interested in two residues. So I have selected lysine and arginine. So once I do this one, is it fine? Are you able to understand what we do? We give a command select. We give some name for the selection here itself, and then put a comma. Then what you want to select? You want to select by residue name, space, which are the residues in a standard 3-letter code. That's all. Okay. Right. Once this is done, so I am just running it. So already it is selected and named it as basic. But one problem is that chain B is also there. Right. So, and that is what it has been done. But anyway, in the basic now, whatever the selections are there, those selections I will make it as a lines so that, and then color them, let's say in cyan. So wherever the cyan color is there, those are all basic residues. Right. Chain B is off. Maybe we can switch on the chain B also. Show as a cotton. So there are chain A, I'm sorry, chain A, chain B, wherever I see the cyan color sticks, those are all either lysine or arginine. If you want to see one of the residues, you can just give one of them. That's all. Okay, right. Suppose I want to see the 50th residue and 100th residue. I don't know what are those residues. It could be alanine, it could be glycine, but somebody says that I want to mutate the 50th and 100th residues, and then what are their positions? Can you just find out? One way is, of course, we can go down here by number and see that. Suppose I ask you, I want 50, 100, 150 and 200. What are these four residues? So you have to select one by one, right? Instead of that, you can go to the command line. So in the command line, what you can give is some name you give. Let's say for that, let's say mutants. Suppose I want to mutate these residues. So I just give a name mutants. And now I go by the residue number 50 plus 100 plus 150 plus 200. So it has generated, so this is the command, command is something like this. So I have selected four residues. I have given a name mutants, just some name you can give. Okay, but this is RESI. I go by now residue number. So RESI 50, 100, 150. Of course, you can add so many but by number. I don't know the actual residue names. So I have selected four residues. Now those four residues will be appearing here as a mutants. Maybe I will give some other color for that. I will give, I don't know, maybe red, and I will make them spheres so that they are very clearly visible. So you can see the red spheres in both the chains because there are two chains. Both the chains can have those residues. You can see here. Wherever red spheres are there, that would be one of those four residues, 50, 100, 150 and 200. So if you know any specific residues which you want to highlight also, you can do that. Generally we do it for ligands basically, on the residues which are surrounding the ligands. Suppose somebody says that, okay, this PLP interacts with the residue 44, 58 and 75. If I don't give you this information, I just say 13, 75 and 55, you can type it as a command and do that. Okay. Alright, so there are many other options. Of course, you can explore all of them. In fact, you can find the distance between two residues. So that is in the wizard. Suppose I want to see the distance between 58th residue and 100th residue. Let's say that there are two maybe the ligand I will choose, that would be better. The ligand show as sticks. The mutants I will just hide. So the ligand is as a stick. So I just want to see the distance between the ligand atom and this atom. Let's say that these are the two. I want to see the distance between them, exact distance between them. I can go to the wizard. There is something called measurements. There are different options. I'm just showing you. You can do a mutagenesis also in this one. Okay. So measurement. I choose this atom from the ligand, and this atom is from the protein. And if I say done, then it will, if I zoom in, I can see that it is 23.1. Remember that pi mole gives in Armstrong unit. It is a standard. So, I'm sorry, it's not at the center. Yeah. So, this is the distance between these two atoms. 23.1 Armstrong. So, if you want to see distance between N terminal and C terminal, or if you want to see the particular ligands atom to any particular residue, that's what we have done here. So, you can measure the distances as well. So, these are some of the very basic things what we can do it in pi mole. In fact, if you practice it more, or you can just introduce to the students, they can practice it more, you can make beautiful movies of that. Like protein is there, the next frame could be the ligand binding over there, the next frame could be the hydrogen bonding, the next frame could be the distances on the hydrogen bonding. So, and then if all the 4 frames they connect it and then show it, then it will be very nice thing that there is a protein, ligand comes and binds, it forms a hydrogen bonding, this is the distance between them. So, actually students are more creative. Generally I don't use pi mole, I just tell the students to make the figures. They will surprise you literally, which you would have, at least for me, I would have not thought that we can present the protein and ligand this way. So they made us very beautiful. I will just give you one example. Okay, one of the molecule, ionic liquids we call them. So the ionic liquids binds to the protein in multiple sites. It's not a single site like what we see. So it binds on the surface. Almost 15 to 20 ionic liquids binds on the surface of the protein. However, all the sites are not equally potential, obviously, right? All the sites will not have the same amount of binding affinity. Some of the sites have better binding affinity, some of them has less binding affinity. How would they, I told the students that, see, I don't want to write this, that selecting that A20, T13, it has a better binding affinity, N15, it is little less, A75 is still less. I don't want to write it. You make a figure, but I want one figure. You don't make a movie and show me that this is better, but these are all I don't want to, because of course the publisher will not accept. If I make a big movie, one movie with I think 10 MB, you can make it. It's not good. I want to show to the reader in the main text itself. I just told the students I have no clue what you would do, but I want one figure where can you show graphically that these are the places where ionic liquids bind more affinity, less affinity, and no binding. There is another thing also. Some of the sites it never binds. What she did was amazing. She made a color palette from blue to white. So it transfers from white to blue. Actually, basically white to blue. So white, very light blue. She made then cyan, then a sky blue, and then a dark blue. So she made a 5 different color palette. She made the binding affinity to 0 to 1. Whatever the binding affinity, she made into 5 different classes. So if the binding affinity is, let's say 2 kilocalories, it is up to 0.2. If it is something is between 2 to 4, it is 0.4. If it is 4 to 6, it's 0.6. Like that, she converted the whole binding affinity into 0 to 1. This is basically a percentage also you can imagine. 0 to 100% she converted the binding affinity. She colored the total cotton surface by that number. So if, and then gave a bar graph. Now if I see the color, then I can say that if it is dark blue, that means here ionic liquid will bind more. If it is white, ionic liquid will not bind in this. If it is cyan, it will bind moderately there, because it's not dark blue, right? So I was just surprised. I never thought that we can present it that way. So just she wrote a small program so that she doesn't need to manually select the residues and these things. So you can do it, you can connect it to Python and do it. So of course students are smarter, right? So if I tell, that's what, I had no clue that how I could, but I wanted to do this, that's all. I told her simply that I wanted to do this, somehow you do it actually. So she made it that way, and in fact reviewer specifically mentioned that, okay, this is a good idea of showing how a same ligand can bind to multiple sites, however the different binding affinity. This is the first time we are seeing that this is made it in this way. This is good for the readers. Though they have given some bad comments, critical comments about others, but specifically they appreciated the figure actually. So if you just introduce and then leave it to them, they can do very unexpected things actually, which we would have not even imagined that we can do it that way. There is a movie option. I think they would enjoy really a good one. So instead of doing something in MS Paint or something, they can actually do it here so that they'll learn more about it. So that is a thing with PyMol, and I would say that I have covered what are the things you can, maybe a 5% of what you can do it in PyMol, 95% I have left to you. So please explore it. That is the only way. Even all the databases also, please explore it, then you would get many more options in this. Do we really have a time for, oh my God. Okay, I think we do not have time for these things, but I will just take 2-3 minutes that what I have supposed to discuss today, which I did not cover anything. Okay, basically small molecular databases, mostly the drug molecules. However, the databases are actually a small molecule database. It's not very specific. There is something called drug bank, which keeps all the approved drugs at different level of clinical trials. So that is a drug bank. But if you want to know about all the small molecules, the best options are, one is PubChem, another one is ChemEMBL. ChemEMBL is what suggested in your syllabus also. And of course, PubChem is also equally good. Yesterday also I discussed about it. I thought I will take this one as an example and explain you. But these two websites anyway, it is given here, you can go and explore. But remember that there is something called SMILES. This is interesting and you should know it. That any molecule can be written in a, they call it as a linear format, line format. So in fact, if I give you this one, of course, if you practice it, you can draw the structure of the molecule. So this is called SMILES format. So it's a linear way of writing any molecule, including the stereospecificity. So these symbols, what you see here, this is whether the molecule, the atoms, next atom has to be read in a anti-clockwise or clockwise. So this means you have to read, these are two anti-clockwise, that means this hydrogen comes from the carbon next in the clockwise direction, whereas this hydrogen comes anti-clockwise to the carbon. So therefore you include the stereochemistry in it. So you can write a linear notation of any molecule. This is very standard, any database uses this. So any linear notation of any molecule, but including its three-dimensional arrangement. So that is what the advantage of the SMILES. Why do we use it? Suppose I have 1000 molecules, if I have to download all the structures and use it for any database, it will occupy so much of space. Whereas I write it, it's like writing 1000 sentences. If I write 1000 sentences, these 1000 molecules are ready for me. So that's why databases prefer this way of expressing these things. Suppose if I get these things for my molecule, I will just quickly show that. I thought you can also come with me, but I think it's difficult now. Say for example, I go to PubChem and take this molecule. I will just type this molecule. So this is basically an anti-cancer agent, so because I was asked to take some drug molecule. So this will give all the information. So you can see at the side, structure, name, what is its drug activity and pharmacology, toxicity studies, and what are the similar other molecules, all the information, so you can get it from PubChem, of course in ChemEMBL also. Okay, I'm just showing one of the examples. And if you search for the SMILES, you will get the SMILES. So what is the advantage of these SMILES? Suppose I want to see the molecules which are similar to this. So I can go to Swiss similarity and I can search the molecules which are similar to this. It's not exactly the same molecule, which are similar. Okay, but those similar molecules are really druggable or not. Right? That is another one. For that, you can go to uh, Swiss ADME, I think you all know about ADME properties, right? So Swiss ADME, where I think network also has a problem, where you can submit this SMILES code and it will predict different drug-like properties. Of course, you can, at a time, you can up to 50 molecules you can submit as a SMILES code. So 50 SMILES code you can submit and it will do it, but it will take time, so I am going for only one molecule, so that it will be easy. So it will give a drug likeness. So any small molecule you can, yeah, that's all. That's all, only thank you, that's all. Okay. So it is done now. So you can see all the drug-like properties. What are the drug properties? What is its absorption? What is it other? Whether it follows the Lipinski's rule, Gold's rule, and Weber's rule. These are the drug-likeness. So that completely you can get. At a time you can submit 50 SMILES codes. So you go for a particular molecule which is good inhibitor but not having a drug likeness. What you can do is you can search for the similar molecules, take all the similar molecules, look for the drug likeness which is potentially can have a better drug likeness. So that is how different modeling can be done. Sorry, we don't have time to do this, but you can, I will give the presentations here. All the links are there. This example is also there. You can try it yourself. Okay. All right. So I would stop here. If you have any questions, we can quickly discuss. Otherwise, you can write to me. My email ID is also there in the PPT. Okay.
University of Hyderabad. So yesterday you had a couple of talks from Dr. Vivek. So I belong to the same department. He is my colleague. I will be showing you. I'm assuming that most of the basic concepts of machine learning and artificial intelligence were covered. So I was asked to show one example of it, how you can use machine learning or AI in any biological problem. So I will show you one of the recent work from the lab, my PhD student's work. In fact, I would say that I simply took her PhD thesis slide. She defended last year. Now she is a postdoc in IIT Mumbai. She has recently joined. So I will be mostly showcasing what she has done in her PhD. So the tool what she has developed is named Magical. She only named it as Magical, which is a machine learning approach to predict genetic interaction in human cancer. I will explain each of these terms. So Magical stands for multi-class approach. So far, I'm not aware whether you were explained what is binary classification and multi-classification. Again, I have a couple of slides for that. To identify genetic interaction in cancer via algorithm learning. So I'll take this opportunity to introduce my department. In the School of Life Sciences, we have 5 departments: Department of Biochemistry, Department of Animal Biology, Department of Plant Sciences, Department of Biotechnology and Bioinformatics, and the 5th one, which was recently formed in 2017, I joined in 2018, is Department of Systems and Computational Biology. And the need for forming this department was that this course, Integrated Masters in Systems Biology, the first listed there, was already there since 10 years. But there was no such department, and this course was taken care by faculty of all the 4 different departments of the school. So sometime it was a problem that there are so many students, alumni, newcomers, but there was no department as such to take care of the students and take care of the syllabus, revising the syllabus and everything. Therefore, this department was formed. Professor H.N. Nagarajaram, who was there in Department of Biotechnology and Bioinformatics, he was then made head of Department of Systems and Computational Biology. And myself and Dr. Vivek, we joined at the same time in 2018, not just before, one year before COVID. So Vivek, as you from yesterday's talk, you must be now aware that he works on plant genomics, metagenomics. He also started working on population genetics. My work is mostly on cancer genomics, and in basic sciences, it's RNA biology. Again, mostly focusing on non-coding RNAs. Then we have Dr. Pramod Rajaram, who is a system medicine and bioengineering person. So mathematical modeling, those kind of work. We have Dr. Momita Sahare. She works on modeling and simulation, docking, simulation, so protein engineering, those kind of work. Dr. Venkat Prasuja, he is a neurobiologist. So his work majorly focused on stroke biology, how stroke happens, and what is the relation of brain and gut, whether gut microbiome decide how the brain neurodegenerative disease would occur. And then we have Professor Gauri Shankar, who was a recipient of Padma Shri Award. He was earlier director of CDFD Hyderabad and many other places. Now he is honorary professor in our department, and his advices are very helpful in our day-to-day science work. So he is a bacterial genetics. So he doesn't own a lab, but he is there, like he keeps taking lectures on human physiology. He being MBBS himself, so he has a better understanding of medical terminology and how to explain it to people like us. So courses which we offer from our department is integrated master's course, which is through CUET UG course. So after 12th, students can apply for CUET UG, and then they can choose IMSc Systems Biology. Then we have Masters in Computational and System Biology, which we started recently last year. So these IMSc students, after completing 3rd year, merge with Masters in Computational Systems Biology. There are few courses which are differing, but majority of computational system biology is covered together. And then we have PhD in computational system biology also ongoing. So about my lab, little bit, what all of us work with, although I will be covering only one topic of it today. So in terms of technology, if you see, we work mostly on machine learning, transcriptomics data, epitranscriptomics data, single cell RNA-seq, network biology, or chromatin organization. And in all of these, majorly on long non-coding RNA. So long non-coding RNAs are those RNAs in the cell which do not code for protein. That's why they are non-coding RNA. They are called as long just because they are more than 200 nucleotide bases. That's a very arbitrary cutoff. I don't know who decided this, that if it is more than 200 it is long, if it is less than that it is small, and then you have short like micro RNA which are 21 nucleotide. So we majorly work on link RNAs, long non-coding RNAs. Shishanya is my PhD student. He is working on identifying whether these link RNAs are transcribed from regulatory region of the DNA, which are called as enhancers, and there are some regions which are called as super enhancers, where there are multiple enhancers together. So enhancers are known by histone marks, so they have very specific histone acetylation marks, and if multiple enhancers are together on the DNA, whether there is a possibility of transcription of this region of the DNA, and if it transcribe, because super enhancers are known to determine the cell fate, we are asking whether the RNA transcribed from this region also holds this kind of property, and if yes, how does it work? So he is working on glioblastoma data. Again, currently we do not have Indian population data access, but we mostly work on the cancer genome atlas data, which holds Caucasian population RNA-seq data. Ananya is another project staff. She is also working on difference between super enhancer and typical enhancer. Then I will be presenting Anubha's work. Anubha was my first PhD student. She had developed this tool Magical, which is based on network and random forest to predict genetic interaction in cancer. There are other tools from the lab which we keep developing. Some are R packages as well, and Ajmal was involved in that. Pallavi and Kirtana, they are also project students. They have completed their masters from our department itself. But nowadays, as you must be aware, that many of these students, they want to go abroad for PhD. So they just stay here, and because they are very well trained and they know computational biology nicely, so we assign them into a project. Even if in 1 or 2 years they are able to produce good amount of data to publish. So they are very talented students, Pallavi and Kirtana. Kirtana recently has got offer from Oxford for PhD. So that's what I was telling, that they know how to handle the project really well and can analyze any sort of data. So they both are working on identifying cis regulatory role of link RNAs. So what we believe that many such paper, for example, you must have heard of ZIST, which is a very famous link RNA which kind of binds to covers X chromosome itself and silence it. So just like ZIST, there is Mallet, there is NEAT1, these link RNAs which are popular link RNAs, and they are studied well because they are expressed well. Something which is expressed well, it's kind of easy to study well. But we think that there are many such link RNAs. If you look at human gene code data, there are around 20,000 link RNA. Just like how you have protein coding genes, you also have long non-coding RNA, and almost 80% of these link RNAs are not characterized. We don't know what is the function of it. One reason could be that they are transcribed and they are very cell type specific, so can be used as biomarker. But it's hard to believe that cell is releasing this or cell is transcribing it just to have it as a biomarker in different diseases. There should be some function of these link RNAs, and many of these, because they are longer in size, they make hairpin, stem loop and all, but we don't know, we cannot predict the function of it based on structure. In proteins, you can do that. You have domains, you can predict, okay, if it has zinc binding domain, if it has metal binding domain, if it has this domain, it might function like this. In case of link RNA, it's really difficult to predict the function. So we believe that many of these link RNA itself, the molecule itself may not have function, and the genome is trying to keep it on the DNA just to have a pervasive transcription. So transcription process is happening that is helping the DNA to open, and the nearby gene is able to take that opportunity to transcribe. What I mean is, in the time of transcription, all the machinery is brought for the transcription, and that link RNA itself may not have a molecule level function, but just by bringing all the machinery and holding it there, it is providing the machinery to the nearby protein coding gene so that the protein coding gene can transcribe really well. So that's what we are trying to prove with Kirtana's and Pallavi's work, again genome wide work. We have some preliminary result there, but again I will not be discussing that work today because it does not involve machine learning. Then Amardeep and Kaushiki, their work, again Amardeep is my PhD student, and his work is to look at RNA modification of link RNAs. That's why I mentioned epitranscriptomics, like you have DNA modification. Similarly, RNA can also be modified, and there are 170 different types of modification. Again, many of these are not characterized well. So we think that these link RNAs, although they are termed as non-coding RNAs, but they do have potential to encode for small proteins. And why I'm saying small? Because they hold small ORFs. They cannot have long ORF, otherwise they will be called as protein coding gene. So they have small ORF, and when we looked into ribosome profiling data, we did notice that in some of the link RNA case, around 3000 link RNA out of 17-18 link RNA, that ribosome do bind to this link RNA in a polysome manner. And why the ribosome should bind there? First of all, we got it from ribosome profiling data. Then we also saw that in mass spec data that the peptides coming, there are peptides coming from these link RNAs. There are some such link RNAs. So we are proposing that some of these link RNAs may encode for macroprotein, and there is role of RNA modification in regulating these. So that's what Amardeep is working on. His PhD work is on that. And Kaushiki had worked on predict. Again, she has used machine learning to predict. Given a gene, if you give the sequence of a gene and tell how many exons it has, if we know 5' is splice site, 3' is splice site, and how many exons it has, we can predict how many transcript it can form. Even without knowing, if it is a novel gene, we don't need to know what is the number of transcript it can form. It's not like if any gene has 3 exon, then each of the exon will pair with each other, you will have all possible combination of transcript. It's not like that. There should be a proper 5' dinucleotide, 3' splice site. What should be the intron length? What should be the exon length? There is something called as branching point. There are a lot of such features which determine whether the splicing will happen and in which way it will happen. So taking all these features, we were able to predict, like given couple of information like number of exon, what is there in the 5' splice site and 3' splice site, we can predict that how many transcript it can form, and that's what we published in RNA biology. And again, Kaushiki was my master's student. Currently she is pursuing PhD in Purdue University. So again, my lab has mostly worked with the help of master's student in their project thesis. So I'm very much obliged to them that they choose my lab for the work, and they continue working, like whatever they have done in master's project, they continue, and once they finish, they make sure that paper is published, they take authority of the work, and then only they leave the lab. I'm happy to give recommendation to them wherever they want to pursue their PhD, it's their choice. So now today I will talk about Magical, which is a machine learning based tool, as I mentioned, and why this work is very relevant to cancer is because targeted therapy is one such approach which can kill tumor cell and spare the normal cell. So we wanted to work on something which can target only tumor cell and spare the normal cell. So if you must be knowing about PARP1 and BRCA1. These are DNA repair enzyme, and in case of, where is the, can I have pointer? Is there any pointer? Something? Okay, I'll go there itself maybe. So as you can see that in normal cell, if PARP is inhibited, PARP is made non-functional or inhibited by any drug, the DNA repair can be done by homologous recombination method. But if you think of a cancer cell where the BRCA1 or 2 has a mutation, so definitely the DNA break cannot be repaired by homologous recombination. And then if you administer PARP inhibitor there is no PARP to repair the single strand break also. So what eventually will happen, the DNA break will remain as such, there will be accumulation of more DNA break and eventually the cell will die. So this is a very well known concept in case of BRCA1 and PARP1 interaction. What you may notice that BRCA and PARP, they are not physically interacting. They are not physically interacting, and that's why it is called a genetic interaction, because the product may not physically interact, but they do show some kind of dependency on each other. So here the dependency is, if one is not there, other is able to take the function. If this is not there, this is able to take the function. That's the dependency we are talking about. So genetic interaction is interaction between two or more genes to give rise to some different phenotype. So here the interaction between BRCA and PARP is leading to cell lethality, and that's what is called as synthetic lethality. That's the most commonly known genetic interaction, synthetic lethality, and this approach has been used in multiple cancer. Olaparib drug and all the Parib's drug which targets PARP inhibitor are given to those patients which are patients harboring BRCA1 mutation. So it works in a way that it will kill the cancer cell but it spare the normal cell, and that's what we want. We don't want normal cell to be killed. So fine, this is very well known. Again, to repeat what I just now mentioned, that if there are two genes, both the genes are wild type, cell is viable. If one gene is mutated, either one of the gene is mutated, cell still remains viable because the other gene takes care of it. Only when both the genes are mutated or inhibited, then the cell goes for lethality. So this is bad for cancer cell because cancer cell dies, good for cancer patient. So this you can understand in terms of drug sensitivity. Which drug will work better in which patient? Patients harboring mutation in BRCA1, olaparib will work good. So you can predict drug sensitivity for a patient. This example just now I mentioned that if single strand break is there, PARP1 can repair it. In normal cell it will be repaired nicely. If PARP inhibitor is used, again in normal cell it can be repaired by homologous recombination method. But if the patient is having BRCA mutation or the cell is having BRCA mutation, there won't be any homologous recombination and it will eventually undergo cell death. Now, the other genetic interaction which I want to talk about is synthetic viability. Here the phenotype is ulta. In synthetic lethality, the cell was dying. In synthetic viability, cell survives. So cell gets some kind of resistance. Again, here the protein product need not interact. This is something called as, again, both the cases it is epistatic interaction. So the two genes are having dependence on each other. Here what happens, again the two genes are there, cell is viable. If one gene is inhibited by drug or some mean, cell undergoes sickness. But over the time, another gene gets some kind of mutation, mostly gain of function mutation, which helps the cell to rescue the phenotype and undergo survival and finally proliferation. Now this is good for cancer cell, bad for cancer patient, an example of drug resistance. You understood the difference between two genetic interaction which I mentioned, right? In one case, cell is dying, in other case, cell is surviving because of the interaction. And the example is between, this is Notch signaling pathway, and here the example is between HDAC and DVL protein. It happens or it happens. So when patients or cell is given HDAC inhibitor, eventually what happens, another gene in the pathway gets a gain of function mutation, leading to rescuing the phenotype of sickness and taking the cell for proliferation. Can you call someone? So what I am saying is not just about couple of pairs. If you look at the relevance of genetic interaction in cancer, there are some genetic interaction. One I already mentioned about PARP inhibition and BRCA1 and BRCA2, and it is already in clinical trial, has been used in breast cancer. There is synergy between BRAF and MEK, these two protein, and it is again in clinical trial used in melanoma. So this is again EGFR and BRAF in clinical trial used in colorectal cancer. These are just list of handful of these, and I have cited the example here. Why sometimes it will be useful is it's not easy to target a protein which is oncogene or tumor suppressor itself, because the activity pocket may be occupied, or the protein itself is really low expressed. So instead of inhibiting that protein which is already mutated, it's good to inhibit some other protein which is taking care of the cell when this protein is mutated. So if you inhibit this protein also, the cancer cell will eventually die. So that's the concept, and there are a handful of these. Over the years, if you look at the discovery of genetic interaction, it was first identified in Drosophila, fruit fly, by Calvin Bridge, and then later coined by Theodor Dobzhansky as synthetic lethality. And then people started looking it into multiple model organisms like C. elegans, yeast, algae. And because of shRNA screen and siRNA screen, now then people started finding many such pairs that if this protein or this gene is inhibited, which other protein takes care of the cell. So by using shRNA screen, they were able to find such pairs. And when the development of CRISPR was there, then again there were many such pairs identified, but again mostly for the proteins of their interest. Suppose I am very much interested in T53, so I will only do it for T53. Why to waste money for all 20,000 proteins? So all these studies which I am showing are very specific to some of the proteins which are of interest in cancer biology. So which tells that, okay, fine, we have experimental approaches like I just now mentioned. Most of these are low throughput studies. Many of these are to find what is there in human or what happens in human cancer. People use yeast as the model organism. There may not be relevant homology between yeast and human, so sometimes it may not work. And again, these experimental methods are expensive. So there definitely is need for computational approaches, and in that the approaches can be divided into statistical pipeline and machine learning. There are some very few network-based approaches also. In all these approaches, the input data is either copy number variation or mutation or expression. I'll go into more detail of it. So now if you look at computational methods, two major categories are there: statistical method and machine learning method. Over the year, there are different tools which in statistical method which have most of these tools are like these two tools are for yeast, and then when the cancer genome atlas data was available, people started using expression data, mutation data. Yeah, it was blinking, but now it is fine. So people started using the mutation data, expression data to again make a statistical model to predict mostly synthetic lethal pairs. So how a statistical model works, the concept is based on mutual exclusion and co-occurrence. So little tricky, but I'll try to explain it with one example. So here is one example of mutual exclusivity. What I'm showing you here is these two genes, EGFR and BRAF. And each column here, the gray color what you are seeing is one patient. It is representing one patient. This is from the cancer genome atlas for Caucasian population. And the colors what you are seeing is different type of mutation. Okay. Now between the two genes, if you look at the mutation, do you see any pattern? Not the types of mutation. I am saying the patients harboring EGFR, are they also harboring BRAF? The patients harboring BRAF mutation, are they also harboring mutation in EGFR? That is the question. Do you see any such pattern that patients harboring EGFR also harbors BRAF mutation, and the patient harboring BRAF mutation also harbors EGFR mutations? Look at this. So these gray columns are, these are all patients. This is disturbing, right? This is one example which I am showing. There can be multiple such examples. But do you agree that there is some kind of mutual exclusivity? That if the patients are having BRAF mutation, they do not have EGFR mutation. If the patients are having EGFR mutation, in very few cases you might see BRAF mutation, but many cases there are no mutation. And then there are many patients which are wild type. So there is some sort of mutual exclusivity here, which means that you will not find such patients or many such patients harboring mutation in both the genes. Why is that? I'll take example of BRCA1 and PARP1. You will not find many patients. There are 1,000 patient data for breast cancer in TCGA. And when we looked for how many patients have mutation in both BRCA1 and PARP1, we could find only 12 out of 1,000. Only 12 patients had mutation in both the genes. You know why? If there will be mutation in both the genes, cancer cell will die, patient won't be patient. Because that's what the objective is. You understood what I am saying. So either you will get mutation in BRCA1, that's why the patient is coming to clinic, because one of the gene is mutated and the cancer cell is surviving because of PARP1, or the patients will have PARP1 mutation and BRCA1 is taking care of cancer cells, and that's why the patient is still having cancer. But those patients having mutation in both the genes, of course the cancer cell will die, the patient will react better, will have better survival, and you may not have those patients in your studies. Which means if you look at this concept, you can identify SL pairs by this concept of mutual exclusivity, provided you have enough number of patients. That's one criteria, because it's a statistical way to identify such pairs. You need hypergeometric test, and for that you need enough data to be confident. In other case, which is synthetic viability, is opposite. You will find co-occurrence of mutation, which means that the patients who are cancer, whichever cancer data you take, both the genes will harbor the mutation. Why? Because it is showing the resistance. Cancer cell is surviving, isn't it? So synthetic viability can be identified by co-occurrence. Synthetic lethality can be identified by mutual exclusion. I hope I made it clear. Okay. The problem with the statistical model is you need number of patients, and it depends on the assumption which I just now mentioned, that you may not see a patient having mutation in both the genes. But it's not just two genes which interact. There are multiple genes. There can be higher order genetic interaction. It's not like this gene is not there, other gene will take over the function and everything is fine. There could be third gene which is also involved there. So third gene mutation can affect the second gene function. Fourth gene mutation can affect the third gene function. So it's a higher order genetic interaction. So we cannot be very sure about what will be reflected by statistical method. Now in case of machine learning, there are tools, existing tools, and most of these tools are trained on yeast data, requires gene expression data, or requires the information of domains. Again, for example, if you want to know whether BRCA1 and PARP1 are synthetic lethal pairs, whether they share the same domain, yes, DNA repair domain should be something similar there. So based on those concepts. The problem with existing machine learning methods were, wait a minute. Yeah. So most of these methods which I am showing you are binary classifier, which means it is able to predict whether a pair is synthetic lethal or not. None of these tools were for synthetic viable pairs. If you have two genes which you are working with, you are trying to use siRNA, shRNA to knock down this gene and see some phenotype. Every time what is happening, the other gene is taking care of the cell and you are not seeing the phenotype. But you don't know which one is the other gene. With two siRNA you should be using. So this is again example of genetic interaction. The two genes are working in redundancy. If one gene is knocked down, the other gene takes care of the cell. So if these tools are used, you will get to know that, okay, this gene and this gene are SL pair or not, but it won't tell you that these genes are not SL pair, but it could be SV pairs. So what we are proposing that most of these tools, if you look at the genetic interaction, if this is SL, this is SVs and these are not, which are neither of the two. Most of these tools, what it is doing, it is making a hyperplane, or it is finding the features which can discriminate between these two sets. Where SL and in not you have these genetic interaction also. So you may not be able to capture features which are discriminatory between SL and SV. But what we propose that there should be a multi-classification approach where there should be multiple hyperplane and we should be able to select features which classify not just two classes but three classes. So example is, if you have a model trained on whether a fruit is apple or not. So features could be, if it is circle, then it is apple, otherwise not. If it is red, it is apple, otherwise not. So circle, shape is a feature, color is a feature, and your binary classification is working whether it is apple or not. Now if you show orange to the model and ask the model to predict, it is also circle in shape, so the model will think, okay, it is circle, tick mark. If by chance the color is more towards orangish and reddish, it may predict incorrect that it probably is apple, because it has not seen any other data set, apple or not. So when it is saying, if it can mispredict it as apple, then the model failed. If it is saying it is not apple, it is not telling you if it is not apple, then what it is. In multi-classification, we want to try with apple, orange and not apple, orange. Three classes. So if you are showing orange, if it is not apple, then it is orange. It is not going to the third class. You understood the difference between binary classification and multi-classification. So again, this kind of multi-classification can be 1 versus 1 or it can be 1 versus rest. And in our practice, our analysis, we found 1 versus rest work better, which is apple versus rest, orange versus rest, and neither of the two versus apple, orange. So that kind of analysis works better rather than doing all versus all. And for that, I'll show you which algorithm we use. So the existing gap in identification of genetic interaction was, we did not know what property can classify SL from SV. I will be using SL and SV now instead of saying it synthetic lethality and synthetic viability every time. We don't know whichever models were there, we were not able to interpret anything from the model that how these two genetic interactions are different. So there were no such papers identifying any determinant features. I hope you have also some lectures on determinant features, how to find determinant features in machine learning. Were there something like that? No? Did anyone talk about features in machine learning? Features, not explicitly. But did you get an idea what is features? Like with the apple and orange example, like in case of genetic interaction also, we don't know what should be the feature to differentiate between this class versus this class. Whenever you train a model, you need to, with your knowledge or existing literature, you should think what feature you want to use for classifying. We did not have any gold standard data set to work with, and whichever models were there, they were trained on sparse or imbalanced data. So it needed a robust, efficient, reliable tool, and therefore these were the objectives which were framed, which is to first use network properties as feature. I'll tell you why in next slide. Then we build a multi-class model for predicting genetic interaction. After predicting genetic interaction of all the human protein pairs, we stored it in a database called as Magical DB, and then we constructed tissue-specific genetic interaction and looked into its relevance to the glioblastoma disease. Yeah. Yes. One problem was there. I will show you in the next slide again. There are not enough SVs data. So one of the class is less known. There are not enough data to train. I'll show you how we worked on that also. Other reason is, although there were these papers talking about that you can use network as the feature, but nobody used the network properties as features to classify these genetic interaction. So again, whatever model you want to develop, you need to know which feature can classify this class to this class, right? So these were some of the papers which we started with, and it was not an easy line for either me or my student. I was also new PI. I still feel that I'm a new PI. I still have less experience in this field. And my student was from computer science background. She did not have any biology knowledge. So she learned DNA, RNA, protein, everything after joining PhD. And now we had to find a place where both of us are comfortable. So she was very good in coding, and I was able to understand the cancer biology part. So we both sat together and multiple discussion, and I'm glad that she was my first student. It definitely matters who is your first student when you have your new lab. So she only found this paper and told me that, okay, ma'am, look into these papers. Everywhere they have talked about that if synthetic lethal pairs, again I'm taking example of BRCA1 and PARP, if you map it onto physical protein-protein interaction network, there are these papers suggesting that they are in one paper it says that it's conserved across different networks. In other paper it says that they are very important genes in terms of centrality measures. In this paper also they have used a little bit of network biology to understand how these genes interact with each other. So why don't we use network properties? This is a typical representation of human protein-protein interaction network. You must have seen in a string if you have used the string database. You won't be able to, like, nobody can understand what is this. It's just a hairball. Lot of nodes, lot of edges. What does it represent? It represents this protein interacts with this protein interacts with this protein, and the edge what you see here, it can be physical protein interaction, it can be functional interaction, it can be based on both are cited in the same paper, it can be both are evolutionarily connected. This is from a string database. But the interaction what we wanted to work was physical protein-protein interaction, where we knew that the two proteins interact, physically interact. Now, you cannot tell which proteins are more important, which proteins are less important here. This is a typical network representation you probably have seen in some of the lectures. I'm making a toy example of it here. To know that which protein is more important and which protein is less important, there are some metric. One common metric could be how many other proteins this protein interacts with, which is called as degree. So here in this example, I can say that J has higher degree, D has higher degree, and that is represented by size of the node. There is something called as betweenness centrality, which is from this module to this module. If you have to pass, you will definitely pass H. If you remove H, the two modules will be separate. In cell also, there are such proteins. The only role of such protein is to connect two different modules. So that's why they hold high betweenness, and that's why they are important for the communication between two different functions. Then there is something called as closeness centrality, which is which node is close to most of the nodes of the network. So just like this, there are 20 other network properties. So we thought, okay, there are a couple of papers saying that network can give us an idea that how synthetic lethal gene pairs are there in the network. So we will also learn about synthetic viable pair. First question, let us ask whether there is a difference or not. Is that synthetic lethal pairs are more central, synthetic viable pairs are more in the periphery, or is it like synthetic lethal pairs are more far from each other and synthetic viable pairs are more close to each other? Very simple question we asked. So this is again a toy example, a network. We took experimentally known physical protein-protein interaction network, no computationally predicted ones. From BioGrid and from string, we took experimentally known along with computationally predicted. There is a reason why we took two types of network. BioGrid network, since it is experimentally known, it may not be having complete interactome of human. We wanted to have another network where we have complete interactome, all the possible interaction of the cell. So imagine this is BioGrid network. And these are the network properties, which just now I mentioned, degree, betweenness. There are many other such properties. And these are known, experimentally known SL, SV and not pairs. Now, first question was, if we place SL gene pairs onto the physical protein-protein interaction network, do they belong to different modules? Are they really far or they are close? And whether SVs are close or far. There is a rationale behind thinking that why this would be correct. Imagine this module is BRCA1 module. If something happens to BRCA, only this part will be hampered. These proteins will not be able to work the way it was working. It will not affect this module. Part still will be able to function. So that's why the rationale is that two proteins should be really far from each other. I did not know what would be the answer for SV. I just colored it like this. We had no idea whether the gene which gains mutation and leads the cell for resistance would be the gene in the same module. That we did not know, but we wanted to test. So first thing, you need to work on the data. From where to get the data? We took data from CGI-DB, BioGrid, SynthLetDB. These are publicly available, experimentally known genetic interaction. There are again no computational predicted interaction here. Whenever you train the model, it is very important to have a clean data, and the data which is you are sure about that is working as synthetic lethal pair. No, these are experimentally known, means either by siRNA, shRNA, like if these two genes are inhibited, the cell undergoes lethality. So I am not doing experiment. These data sets are there in these databases if you want to refer. So first we took all the experimentally known SL and SV pairs. SL pairs are shown as this color and SVs are shown with green color. Okay, we have SL and SV, but the problem is we do not have the third class, which is not, which means which pairs are not genetically interacting. How do we know that? I will say that okay, this gene and gene X and gene Y are not genetically interacting. After 2 months, somebody else will publish, no, X and Y genetically interact. How do we know that which pairs will never ever in any condition will genetically interact? We don't know. So to make a negative data set, it's a very difficult task. So what we did, we had this experimentally known pairs. We took all the, so in BioGrid you also have physical protein-protein interaction data, you have genetic interaction data, you have list of all the human genes. So we took list of all the human genes, including protein coding or link RNA, there are not many. So we took all the genes from BioGrid, suppose genes or proteins, which whatever you say, A, B, C. So with all the proteins, we made possible combination. First was that step, making all the possible combination. Then we removed known genetic interaction from there. For sure, not data set should not have something which is actually genetically interacting. Remove it. So we removed it. Then we got another data set where the genetic interaction is known in East. So people might have worked in East and have referred that since these genes are genetically interacting in East, the homologue of these also might interact in human. Why to have that doubt? We removed that also from our NOT data set. So that is also not there. After removing, we had millions of pair. Now, in one hand, we had like around 1000 SLSV, and other hand, we had million of NOT. Here comes the problem of data imbalance. If you train something, again, when I'm saying training a model, machine, if you expose the machine to this kind of data more, so the training will be really good in saying something as not. You need to have balance in the data so that the model is learning from both positive and negative data set. It's just like how if a baby sees something more multiple times, the training will be more on that. So similarly, machine also, which you are trying to train every time, that if this is the shape, this is the fruit, this is the color, this is the fruit. So the training should be in same from each class. So I'll come to that problem how we solved. Once we had experimentally validated SL and SV pair and the NOT data set, we mapped it onto the network, physical protein interaction network, and we learned about what are the properties, all the 20 properties I mentioned, how are they different in SL, SV and NOT. Now, every time I'm talking about two genes, BRCA1 part 1. So in the network also, when I talk about degree of BRCA1 in part 1, I will have two values. Suppose BRCA1 is 20, part 1 is 30. So I cannot have two values for this interaction. I have to have one value for it. So you can either take average of the two, you can take median of the two, you can take maximum of the two, you can take like whatever metric you can think, sum of the two. But you have to come with one metric for that pair. We did like that for SL, SV and NOT also, and look for this is average degree. So we took average. This is average degree of all the pairs which are synthetic lethal pairs, synthetic viable pairs, and not synthetic lethal and viable pairs. First plot, just pay attention to the first plot. Although it does not look very different median wise, but distribution wise this is higher than this, and again significant p-value, because you are talking about thousands of data points. Even a minor difference also makes a difference here. SLs are definitely, SLs and SV both are more central to the network, have higher degree than NOT. They hold higher betweenness. In fact, SLs are more between in the network than SVs. The genes, the SL pairs are far from each other. The shortest path between the two genes are higher compared to SV. That's what we were trying to ask question. SVs are more closer. So just like that, we looked for other properties also, and we thought, okay, now we have a feature which we can use to train the model. So that's why. Yeah, no, I'm not saying we will take average degree only. This would be one of the feature, but I'm saying with this just 5 graphs I'm showing, but there are 20 such properties. So what I'm saying is, in some cases you do see differences. So we will now, we were thinking that, okay, can we use network properties as feature? So here we thought that there are some of the properties which are differing. So definitely some of these properties have discriminatory power to classify SL to SV. So you will notice that average degree will not come as discriminatory one. It won't come. So it will be removed from the model training. And many of these properties, the 20 properties I was mentioning, so these are the properties name. So there are shortest path is number of paths between two nodes. Eigencentrality is you yourself do not have lot of friends, but you know Modi ji. So you have high eigencentrality. You know somebody who is very famous. So you will hold high eigencentrality. Similarly, in case of protein-protein interaction also, the protein itself may not have lot of connection, but interacts with very important protein. So like that, there are these properties, and these are very well correlated also. Since many of these features are correlated, You cannot have all the features in model, which means if something is very, very well correlated, for example, average betweenness and here you have shortest path. Wait a minute, shortest path, average betweenness. Yeah, average degree also, average degree and average betweenness. It's highly correlated, positive correlated, and it's significant also. Why to have two properties which are highly correlated as discriminatory feature? That's why we need machine learning, not just to train, also to identify which features are good enough, discriminatory enough to classify two classes or more than two classes. And we will not just learn which properties among these are good enough to classify, we will also be able to interpret our model that how SLs are different from SVs. So next objective was to build multi-class model, and for that we use random forest, which is collection of different decision trees. Have you, like, I don't know whether the class had, any class had random forest or SVM, naive Bayes, these algorithms? No. So there are some known algorithms in machine learning, and most commonly used ones are SVM, support vector machine, random forest, naive Bayes, KNN. These are machine learning algorithms which are mostly used in biology. If things are not solved by linear regression or logistic regression or regularization, people go with machine learning. And in that also random forest is commonly used. These are classical methods. If this also does not work for learning and prediction, then people go for deep learning, neural network and all. So what is random forest? Random forest is collection of trees, decision trees, where when you show random forest, SL pairs, SV pairs and not, and all the properties, it will try to learn from the properties. Okay, if degree is this and betweenness is this, shortest path is this, and addition is this, then this pair is SL. Okay, if degree is this, betweenness is this, shortest path is this, then this pair is SV. So like that it will learn from each pair, from each class and from each decision tree. So that way it will learn that which features can classify SL from SV and SL and SV from not. So Python and R are, people also use MATLAB, but nowadays because Python and R are freely available, you do not have to have license for MATLAB. Python and R have inbuilt packages which if you install, like in R the package name is caret, if you install the package, load the library, you can use the function random forest, feed in the data that these are SL pairs, these are SV pairs and these are not pairs. So you need labeling there. For each SL pair, what is the degree, what is the betweenness, what is the shortest path, what is adhesion, what is cohesion, all the 20 features. Similarly for SV pair, similarly for not. Iteratively it will learn, the random forest will learn from the data and identify combination of which feature is good enough to classify. Have you ever done any programming? Are you interested to learn? That is another question. If anybody in your lab or any student in masters, if they are interested and if you can guide them, together with them you can also learn. It's not difficult at all. I mean, R is in fact can be easily done in Windows also. In one of the FDP session, I challenged myself to take class on R programming, and it was not very smooth though, but I just wanted to have this feeling in all of us that anybody can program, anybody can learn. So you just have to take out few days of your time, and I know we teachers are always busy. I totally understand that point, but if you're really interested, you can do it. And if your student does it, you will eventually learn. So how we developed Magical? As I said, we took data from CGI DB, BioGrid and Scintillate DB. Look at the number of SLs and SVs. a huge difference, imbalance in the data, right? I was talking about it. And at the other side, we have not, and we are mapping it to the network. We are finding network property, and using random forest, we are finding which combination of which property is good enough for classification. And that's what we are calling it as magical, which properties are good for classification. And we found 5 such property and use that for prediction. Now, I was talking about imbalance in the data set. You can have one class with huge data, other class which is minority group. So you can balance this way that you can oversample this class. If you have 200 of these and this is 2000, so you have the repetition of this 10 times. That way the machine, random forest, will learn equally from this and this. The problem is there could be overfitting because you are just manipulating data here. You are just oversampling it. It may not be real. Only that 200 is repeated those many times. So machine is every time seeing the same data. Other way is, if one class is huge, other class is less, to undersample is it. Now problem with this is that even though you had good enough number of known, experimentally known nice data, you are throwing it away, wastage of data. So could be underfitting. Both are having a big problem here. There is a way out. What SMOTE algorithm does, again SMOTE is available in R as well as in Python. It does both. So it takes minority group and produces more number of minority group and tries to balance data with both undersampling and oversampling together. So although it does not look like sampled really, balanced really well, this is just one time when she is showing it here. We did it 100,000 times just to see that whether we are getting a balanced data or not. So every time when she was doing it, look at this, this is 3,000, this is 9,000, this is 26,000. We are trying to reduce 26,000, almost half. We are trying to oversample SVs, almost double, again reduce not. So we did this 1,000 times to understand how the balancing would affect the accuracy of the model. Now since we have to balance 1,000 times, it means we are running random forest 1,000 times. So we are developing 1,000 models, and 1,000 models will have different accuracy and score. I'll show you the result with 1,000 models, how it looks like. Before going into that, I mentioned that since we are working with 2 genes and we have 2 values, you can use average, difference, maximum, minimum, summation, whatever you use. The accuracy of the model, F1, precision, recall, all these values will remain same. Doesn't matter which metric you choose. We have used decision tree, k nearest neighbor, naive Bayes, random forest, different machine learning tools, and random forest was the best among all the classical machine learning. Among the properties, when we ran random forest, we found the shortest path to be the most discriminatory one. So if we know the shortest path between 2 genes, it's good enough to classify whether the pair is synthetic lethal pair or synthetic viable pair. And there are these properties ranked based on its importance. So if you remove this property, how much it impact the model accuracy. So this graph shows that if you do not remove any, then accuracy is 80%. If you remove betweenness, accuracy drops. If you remove average neighborhood, it remains almost same. If you remove shortest path and adhesion, it drops a lot. So shortest path definitely plays an important role. Adhesion is a property where it tells how many edges you need to remove to separate the 2 modules. So which is again very similar to shortest path. Okay, as I said, we did 1,000 times sampling. I mean, we generated 1,000 models to have a balance in the data set. And for all the 1,000 models, the accuracy ranges from 83 to 84. So model does not change a lot in terms of accuracy. And in all the 1,000 model, these properties, network properties, again shortest path, neighborhood, like how many neighbors are shared, what is the betweenness of the 2 nodes, how many neighboring nodes are connected and making triangle, and adhesion, how many nodes needs to be removed to separate the two nodes in two different modules. These 5 properties, if you see, were picked as the topmost property by most of the model. So 1000 models, and shortest path is ranked as first, like very important feature in almost all the 1000 model. Similarly, average neighborhood was picked by almost 90% of the model. So we thought we can easily give away all these properties, and these properties are good enough. We tried removing adhesion also, it marginally changed the accuracy. So we chose these 5 properties and we called it as magical, where we chose the discriminatory properties to classify synthetic lethal from synthetic viable from not, these 3 classes. And again showing the similar graph, but now this time only for the discriminatory properties, and you can see in many of the cases, here you may not see difference, but the difference is this versus this versus this, a huge difference. Again, when you're talking about more than 2 classes, it's not just about whether it is differing between these 2. Even if not is being classified really well, that also will be picked. Like here, triangle means if you have 3 friends or if you have 4 friends, whether they are also friends with each other. If they are also friends of each other, then you hold high triangle value, which means you are in a connected group. In case of protein-protein interaction, it means all the proteins are part of a complex. They are forming a nice cluster. So we learned that SL pairs are more central compared to SV pairs, and some of the properties which we call as pairwise network properties, where you have number of edges between 2 nodes, or how many nodes needs to be removed. So those properties are more discriminatory than the rest. How did the model perform? Now I showed you the question which can be answered in biology. Using machine learning, you can predict 3 different class. That was the question. You need training data set. That I showed you how to take training data set. You need features. I showed you we took network topology as the features. You need discriminatory feature. I showed you how among all the 20 properties, we picked 5 properties as a discriminatory feature. We used var imp function of random forest to pick those. So every time you remove one property, it will show how it impacts the accuracy. Now, this is fine, but how good the model is? Whether model is good or not is shown by ROC curve. This is a typical representation of any model which shows that if the what is the sensitivity of the model versus its specificity. So for every false positive, for every true positive, how many false positives are there? So that kind of representation. So higher the area under the curve, better is the model, higher is the accuracy. So what we saw, that whether the magical is trained on experimentally known physical protein-protein interaction data set, or it is trained on experimentally known plus computationally predicted physical protein-protein interaction data set from string, both the models, magical core and magical combined, with the 5 properties are able to predict something which is actually SL as SL. So these pink are labeled as SL, and our model is also saying it as SL after getting trained on it. So the model is working well in the training data set itself. It should work well. But compared to the existing paper, which we saw some discrepancy also, that one of the papers said that SL pairs are closer in the network compared to non-SL. And we found completely opposite, that SL pairs are far compared to not and SVs. So reason could be this is trained on very small data set. Other reason could be that here the not part can be SVs and many other genetic interaction which they did not mention. And this was also published in PLOS Computational Biology. So that's how we argued that ours is trained on thousands of SL and SV pairs. This is trained on 400 SL and not pairs. So and again not trained on balanced data set. Here we have balanced it. So we ourselves took all the properties which they are claiming as discriminatory property, and we showed that magical is working better than slant. The name of the tool is slant. It came almost the same time when we were working on our project. So again, my student came running, and I think we are scooped. And don't worry, if they have published in PLOS Computational Biology, we have a strong reason to write to editor that readers of this journal is very much interested in this kind of work. So please do review our work as well. So we took it positively and submitted here itself. Then we move to see how magical is able to predict something which is known by CRISPR study. So this is one of the paper where they have, what they have done is, they have inhibited ATR gene and looked for which genes are, so which genes are showing negative Z-score and positive Z-score. Negative Z-score means these genes become important for the cell when ATR is inhibited, which means these two genes are redundant genes, and the cell is dependent on this gene when ATR is inhibited. So SL pairs and SV pairs, and we found that magical is able to call most of these pairs, like out of around 5,000 pairs which with CRISPR they were able to identify, magical is able to identify most of it as synthetic lethal pairs. So what point I want to bring here is, you need not spend money on CRISPR, and you can use magical first to identify this pair. Here, after investing so much of experimental time and money, then people were able to identify this pair, which magical was able to predict without consuming much time. We looked into other data set, which is DepMap. DepMap is a data set of, for each gene, with whatever gene is of your interest. This data set has CRISPR screen for all the genes. You inhibit this gene and which genes are important for the cell now. So that way, if inhibit this gene and the other gene become important for the cell, it means these two genes are SL pairs. Based on that, we ran magical on the data set, and we found that magical is able to find most of these pairs with accuracy as good as 83%. Then we looked into patient data. We went back to the Cancer Genome Atlas data, and we saw that if we take one of the predicted pairs, so we found that NPRL2 and EP300 pair is synthetic lethal pair. Never been studied in any cancer, or people have not reported it synthetic lethal pair. But if we take patients harboring mutation in these two genes, we found that patients are doing really bad. They are dying. How to read this kind of graph? This is survival plot. In x-axis, you have overall survival. In y-axis, you have number of patients surviving. So in the beginning, all the patients would survive. As the time passes, after 35 months, for example, the patients harboring mutation in the two genes, only 40% of the patients are surviving. Whereas after 35 months, patients having wild type of the two genes, almost 60% or 65% patients are surviving. So you can say that these are poor survival patient and these are good survival patient, that way. So this pair with slant existing tool was predicted as SL, but TCGA also is saying it is SV because patients are dying more if there is mutation in these two genes. So co-occurrence, and magical also predicted is SV. So we were doing something very similar. We were able to find what was been identified by TCGA. This pair again is opposite, where patient harboring mutation in the two genes are almost not dying. They are doing really good. Patients are having mutation in these two genes, but patients are doing better than those patients which are having wild type. And it can happen only in the case of synthetic lethality, and that's what we noticed between the two genes. Slant called it as NOT, TCGA with mutual exclusion called it as SL, and magical also called it as SL. So we got confidence that what we have constructed, the model, it is working good. in pan-cancer study, not specific to one cancer. Okay, so now we wanted to know the pair we are talking about, BRCA1 or PARP1 or whatever pairs we identified, whether they share lot of pathways. And it looks like SL pairs, since they are far, they do not share lot of pathways. It looks like BRCA1 and PARP1 both are DNA repair enzyme, so they share lot of pathway. But it's not like that. They are far and they have very few pathways common, whereas SV pairs share more pathways. So in terms of representation in a network, SLs are far from each other. They are part of different functional module. SVs, which are drug resistant pairs, if one gene is inhibited, the other gene which gets gain of function mutation is mostly the gene of the same pathway. That's what we proposed in our work with our study, and we published it. Then, since we had this model, we ran it on to the all possible human proteins. So we made all the possible pairs and ran. It took 4 months time to run it on all the pairs on server, 256 GB RAM server, and then we hosted it on Magical DB database. We are yet to publish paper for the database, but you still can have access to it. It's on our lab website also. You put your one gene name, you put two genes name, it will tell you whether it is SL, SV or not. If it is one gene, it will give you all the pairs for that particular gene. It can do it for multiple pairs also at the same time. And these are the database structure, how we made the database. We took help of BE student, engineering student from SRKR Engineering College, and those students, they come for 2 months and they did a great job in making the database. Now, what I have shown you so far was pan cancer. I did not talk about a specific cancer, although I took example of breast cancer and again. You may ask that, no, if it is same in all the cancer, then olaparib should work in every cancer. But that's not true. Olaparib works in breast cancer, ovarian cancer, but does not work in other cancer. Because this genetic interaction is also cancer specific. So we thought, okay, let us make one context specific model where we will take only those SL, SV and NOT which are specific to brain, which is known to work as genetic interaction, synthetic lethal or synthetic viable, only in brain. We will take network properties only from brain tissue specific network. We will map it onto the brain network, and we will take the same 5 properties, and we will see how good we are able to predict. And we were able to predict good number of SLSV pairs, and this is a beautiful example. I want you to pay attention here. RECQL is helicase, T53 is tumor suppressor. RECQL is known to transport T53. I don't remember which organelle, but it does transport T53. Now, again, this is a KM plot, survival plot. Look at it. Patients harboring mutation in these 2 genes, shown with this purple color, are doing better. Read this graph like this. Like after 60 months, almost 50% of the patients are, no, at least after 50 months, almost 50% of the patients are alive. For blue one, if you look at after 50 months, only 30% of the patients are alive. There is no reason why patients, these are all patients harboring mutation in these 2 genes, are doing better than the patients having no mutation in these 2 genes. It could be only because these 2 genes mutation is favoring some kind of cell death, tumor cell death, and that's why patients are doing better here compared to this. I know I am claiming just based on 2 genes, but it's really difficult to predict something of higher order, more than 2 genes, because we do not have training data set also. So how to get the features. And this is reported in glioblastoma cells. We found it from magical CNS model, and then we looked into literature that in 2020, it is shown that RECQL for suppression either by siRNA or CRISPR correlates well with increased temozolomide sensitivity of p53 mutant glioblastoma cells. So if these cells are having suppression of RECQL4, then these cells show increased sensitivity to temozolomide sensitivity of p53 mutant. So these cells again are p53 mutant. So p53 is not working in these cells, and now you have RECQL4 suppression also, making the cancer cell really sick, and now you treat with temozolomide, the cancer cells die. So this kind of information can be really useful in cancer targeted therapy. This is opposite between BRAF and PTEN, where patients harboring mutation in these two genes are surviving worse compared to the ones which are wild type. And again, it is reported that these two genes are in resistance. One work we did for application of MAGICAL, where we have identified synthetic lethal pairs in glioblastoma. I will not go into detail of this work, but we identified which cell type of glioblastoma is more tumorigenic than the other cell type. First, we used single cell RNA-seq data and we identified different cell types, and we found that astrocyte based on synthetic lethal pairs show similar pattern as tumor. So we are proposing that astrocyte might be the tumorigenic cell type in glioblastoma. This work is still under, we are still working on it. I have not yet submitted it. I am not getting confidence to submit it. There is still some work left here. So why are targeted therapeutics still in queue and not effective? First is incomplete penetrance. So inhibition of two genes, I am saying cell death, cell death, cell death. It may not lead to cell death. It may lead to cell sickness. The cancer cell may become sick, may not die completely. As I said, there are other genes also involved. Genetic background of each of us are different. Even for patient it is different. We don't know what is there, like it's not just BRCA1 mutation, right? It can be some other mutation which we may not be aware of, and that is very specific to that person. It is context specific. Something which works in one cancer may not work in other cancer. We do not know whether other third gene also might be interacting. The two genes could be SL, but other gene, when it comes into interplay, then it becomes SV. So A and B interact, it is synthetic lethal. C comes, now it becomes synthetic viable. So we don't know that. We do not have enough data to work with. Again, there is cell type specificity as well. Something which is SL in AML, the paralog of it is not SL in other cell. One of such pair between BRCA1 and USP1 is already in clinical trial, not from our prediction. It was already in clinical trial. We just looked into which pairs we have identified as SL pairs with a good score is in the clinical trial, just to gain some confidence, and we could find that BRCA1 and USP1 people are working on it to for the targeted therapy. So future direction can be again higher order genetic interaction. We are yet to understand it in a broader sense. So with that, I will stop, and I am on time. I was asked to take till 1:15. This is my lab. I already introduced most of them. We make sure that whenever we take lab pick, we are all in same color dress. Whether boys of the lab they like it or not, we make them wear the same color for that day. So every time we have, for every year, one year blue color, other year black, some other year white color, something like that. Again, something which they are comfortable wearing it. So Nilima is the new PhD student who has joined. She's not in the pick. I'm yet to take the fresh pick. And as I said, my lab is always full with master students, and I'm really grateful that they choose my lab for the work. I have these project staff. The ones which are bold and darker in color, they are present student of the lab. These are my collaborators. I might have forgotten to mention few, and these are the funding support. I'm really grateful that I have currently I have good amount of funding support. So I'm now moving towards experimentally validating my results. Of course, not in my lab. My lab is computational lab. I have never handled a pipette also. So most of the work which I do in collaboration with other faculty of School of Life Sciences or NCCS. So they are helping me with this. And thank you for giving me this opportunity and listening to me. Any question? Was it little clear that how to develop a model? I know the coding part is missing there, but if you have this idea that you first have to identify the class, you want to classify what to what, you need to understand the features, what feature you want to use. You can use any machine learning algorithm to train. If you wonder from where to start, Kaggle is a database, Kaggle, from where you can download lot of data set. And you can start as simple as taking all the blood report. So whether level of oxygen, whether RBC level, WBC level, whether it correlates to some disease. Any disease you can pick. So this is one common thing you can start with. Out of all these features, which can predict the disease well. So this can be your data set. You input this file to any of the programming language, either Python or R. Use any of the machine, either random forest or SVM. In the beginning, I mean, although random forest is something which people still use a lot, it's a very simplest form, simplest machine learning which you can use. Train the model and see how good the prediction is. Once you are able to develop a model, then you can also find which parameter from all these is able to predict something. You can take diabetes, you can take high blood pressure. You will get some model. I am not assuring you that the model would be the best model, but you will get some confidence. Yeah. Then no question? Okay. Thank you.
Can you hear me now? Can you hear? Now? Thank you. Okay. So you have been they're talking a lot about data sets and what are the different data sets and all that, right? So data set is nothing but a collection of examples that you are trying to learn from. So before going to all this, let's talk about an imaginary thing or just a scenario. When you are teaching in class, you have a set material, you have a syllabus that you are teaching, and you give them a material, you give the students a material, and they learn from that, and you ask questions from the same material. Right? So consider that material is your data set, and now you have a question bank. Say 1,000 questions. You won't give the whole question bank to your students to learn. You keep a set aside, you give them maybe some easy questions to learn, they learn from that, and then in your final exams you give us a set of questions that you have kept separately. So why do you do this? If you give everything to learn, the students will memorize everything, they will not understand the concept, they don't even have to understand the concept. Just memorize everything and they know, if this is the question, this is the answer. Blindly anyone can write. But that's not how a machine learning works. We are trying to make the computers learn from our data, patterns or things that even we cannot see. So it has to learn those patterns and then replicate them in a real life scenario. So from your past experiences, you predict how the future can happen. So similarly, an ML method or an ML program, it tries to learn from whatever data you give to that, and from the learning, it will predict how the future may happen. So to learn from a data set, it needs a data set, right? So I have given 3 examples here. One is house prices, spam detection, and image classifier. So house prices, what are the different features that you will be looking for when you buy a house? So the area that it has to be, what kind of a house it is, like a 2 BHK, 3 BHK, whether you have balconies or not, how big it is, the square feet, how far is the schools or how far is the shopping complex. So these are things that you would look for when you buy a house. And based on the locality, based on the features that are nearby, the pricing, the rates for the house will be different. So you decide, you try to compromise between the location or the price. Right? So even when you negotiate, you have to know the advantages and disadvantages of that house. So something similar, when you give a machine learning algorithm, just the the location or the vicinity of the hospital or a school. So these will decide how much the house will be valued on. So when you give the machine learning algorithm, you give a data set of all these features and some past houses that have been sold, their prices, then it can predict or learn from there. If the house is in this area, then this will be its price. So you give a learned data set, so you give the house prices and the properties, and then in future when you want to buy something, you know the properties, you ask the machine learning algorithm, if I have a house of these properties, then what will the price be? So that's how it's going to learn. Okay. Similarly for spam detection, we keep getting a lot of spam emails. We don't know if they are spam or not. If we know, like, we are safe. If we don't know, then we are not safe, right? So there are rules that you define saying if someone is asking money, then it is a spam. So you define a rule saying if they are asking money, then it is a spam. So a machine learning algorithm can do that. If you have, say, 100 emails in your past few years, give those 100 emails in the ML algorithm and you tell, learn these patterns. If a mail comes of this quality, then it is a spam. So you label them as spam. Now similarly, image classifier. So you have pictures of cats, you have pictures of dogs. They have different features. You can learn from each feature. You can see a photo and you can realize whether it is a cat or a dog. Now normally we can do that because our brains know how to recognize these features, but the computers don't have brains, but we are trying to make it understand, make it learn. We say these are cat images, learn how a cat looks like. These are dog images, learn how a dog will look like. Now once it has learned, you give a new data, then it will tell you whether it is a cat or dog, right? Now we keep telling it is learning, it is learning. How do we know if it is learning or not? You're just giving in some data and it gives you some prediction, some answer. So we don't know if it is learning or not. So how do you test if it is learning or not? That's where comes this. So that's where comes this training and testing. Okay. So when you say learning, there are two types. One is memorizing, another is learning. Memorizing is something that we don't want. Even with our students, we don't want them memorizing. We want them to understand the concepts and then apply in reality. So similarly, even for machines, we are trying to make it learn, not memorize. Right? So just like the example I said, if you have a question bank, you don't give them all the questions, you keep a set separately, you give them some questions to learn from, or they'll know what to expect from the exams. So that expectation you create from a small set of questions, and the rest of the questions are kept aside for later exams. So some like when you have to do this to train them on a set of examples, and then you test them on something that they have never seen before. So the same scenario applies in machine learning also. You don't let the system or you don't let the algorithm memorize everything. You make it learn from a sample of data and then you test it on another sample. So the sample that it learns from is called a training set. The sample that it tests on is called a test set. Okay. So how do you decide what goes into, or okay, before that, why do we need to do this training or testing? So if the ML memorizes everything, then it leads to overfitting, which means it cannot think beyond the data. Whatever you have given, that's what it knows. It doesn't understand what goes on outside this data set. So your question bank of 1,000 questions, that's the only part that the student will know. They'll not know to apply that knowledge in real life. So you should not do that. That's called overfitting. You should make them learn, make them generalize the concepts. So generalizing is you learn from your experiences and then adapt to apply in the new data, in the real scenario. So how do you do that? How do you do this training and testing? So you don't have, like, we are all limited to the amount of data that we have. We don't have very large quantities of data. So with whatever we have to make it sufficient for a proper ML model to work, right? So we need to utilize what we have in an efficient way. So for that, we should know how to do the testing and training set splitting. So there are three commonly used ways. First is just a train or test split. Second is a train, validation and a test split. Third is a cross validation. So there are three ways you can do this. So the first is just a training and a test set splitting. So you have a data, you just split that into two parts. One part you use for training, another part you use for testing. Now this ratio of training and testing, you usually keep more in training, less in testing. So it's 70-30, 80-20, 90-10, 85-15, how strict you want your data to be. So if you give more on training, less on testing, then your model is really strict. So it learns a lot from your training data. If you have a balance between the two, then you are generalizing. Means it can learn the patterns, not the actual data, and it is able to predict on other real life data. So you're I keep saying testing or predicting and all that. So how do you measure the performance of an ML model? So you have there are accuracy metrics if you say species recognition or the image classifier cat and dog. If the from the training it keeps learning if it is a cat or dog, and when you give it test data, it will tell you if it is a cat or dog. If cat matches cat or a dog matches dog, then it means ML has learned. If it says cat as dog, then it has not learned. Right? So your training with say 70%, testing say 30%. So from training it tries to recognize the images, and the 30% it will tell you whether the predictions are correct or not. So what is training, validation and test splitting? So here a job is done. You can do a simple training test set and it's done. So why do you need another one? Training, validation and test set. So here training takes a slightly lower percentage, little more goes in validation and test set. So test set is something that has not come out yet at all. Say it's like a future prediction, right? You have a training set, you have a validation set. You use your ML model to first learn from training set, check whether it has learned or not from the validation set. If it has learned, then see if the model works or not. Put it in a real life application. That's the test set. So test set is not linked anywhere in training or validation. It is a entirely kept alone set, something like out of syllabus. So it just stays out. You don't use it anywhere in your model building. So you keep refining your model entirely with the training and validation set. At the end, once everything is done, you're confident that your method has learned well, then you go and put it on a test set. Then you'll get a real idea if the model has learned or not. Right? And these two methods will work when you have sufficient data to split it into training test or training validation and test. If you don't have so much data, if you have the data is very limited, you can't take the it's insufficient. You can't give half the data into the validation and only use half for training. It's already insufficient. You keep aside half. That's not going to happen. So you have to make use of whatever is available. So we do something called cross validation. So what cross validation does is, it splits your data into smaller chunks of equal portions, say 5 groups. You have 100 data points, you split it into 5 groups of 20 each. Use 4 groups to develop your model, use the last group to test if it works or not. Right? So this again, you don't have the you can't let one group away entirely, right? You need that also for training. So you keep rotating. Say you have 5 groups here, you keep first one as the test set, learn with the 4, test on the first one, then do another round where you will keep second as the test set, learn from other 4, use second as a testing. So like that, if it's a 5-fold, then you do this 5 times by using each group as a test set. And finally you average on all the results. This is called cross validation. So yeah, say you have a question bank, 1000 questions, you keep aside 30, you use only 700 questions for learning, give the 300 as the exam. So that's training and testing. You have 600 on training and 200 you use it for mock exams and use it for final exams. So that's called train, validation, test. So the 3-part splitting. This is a cross validation. So you have 5 groups of same data, use one of them as the test set, use other 4 as the training set, keep rotating, do this 5 times and finally average all the results. This is called cross validation, and this you will do when your data is like the initial data is less. You can't afford to put one whole data into test set. Right? So you use train test or train validation test when the data set is slightly larger, but when your data set is very small, you use only cross validation. But the cross validation is slower, slightly slower, because it has to do the same thing 5 times or times you decide and then average that. Rest of them needs only one random splitting. Okay, so what ultimately we are trying to do is always measure how the model performs based on the data that it has never seen before. So that's the whole concept of splitting your data into training and test sets. Okay, now I guess you have been using orange for a while, so we'll see how this happens in orange. It's downloaded and installed, but it's not opening. So we'll use the iris data set. Alright, so from after loading the data set, you know how to see the data. So you create a data table widget and from there you are seeing the data. Now you see there are 150 data and 4 features, right? Now we have to split this into test and training set. So from file, you create a new widget called data sampler. Yeah. Okay. Now double click on the data sampler. You will see 150 instances in the input data set. Now it's asking you how do you want to. So you give either 70% for training and rest for testing. You move the slider, change to whatever you want. For now we'll just try with 70. Now you can use this for testing and training splitting, 70 and 30. Now just click on, create a new data table again. Okay, you loaded the data set. This is just to see how the data set is, right? Now now this is not needed. I'll remove this. So you have your data set. Now create something called data sampler. Okay. Just right click and it will give you data sampler. Search in that, it will give you data sampler. Or you can even click and drag. It will show you this. Then you search for data sampler. Now this, yeah. So here you have the data set loaded. Now from file, you create a new one called data sampler. So data sampler is the widget that is going to let you split the data into test and training set. Now double click on data sampler. It will ask you how many samples you want to do this, split this into. Now I am showing 70% for test and training. Okay. Now I want to see this data, see if this splitting has happened or not. So for that, I am creating a data table from the data sampler. So the connection that you have here, it says data sample or the 70% that you filtered, that data is there. Create another one, another data table. Now change this data to remaining data. Yes. Yeah. Okay. So I created second data table to see the test data. Now if you see, yeah, this link, this thing here, it says data sample data, right? So from here you see data. So from file, whatever data is there, everything goes to data sampler, right? Now in the second one, you are seeing data sample data. So data from this goes to this, right? And it is asking data sample, which means it has output of this data sampler. Now we asked to do 70%. So it will have a 70 and a 30. So we need to see two data sets. So I create two data tables. Okay. Now I want to put training set in this and test set in this, right? So for that I double click this. So you double click this, you will get this data, this dialog box. Yeah. Now remove this connection and put remaining data to data. Okay. So now this change to remaining data to data. So your 70% will be in this 105 instances and this will have 45 instances, right? So initially you had 150, right? So your original data set had 150, this is your 70% and this is your 30%. Right? So this is, if the tool has split your data into two parts. Now if you want to change this, ratio, you can go back to this data sampler, change it to whatever you want, say 80% sample data. This changed, it changed from 105 to 120 and 30. Instead of 70-30, now I am showing 80-20. Now you can do the same cross validation here also. You can split your whole data into 10 folds or whatever number of folds you want. And just click sample data. Yeah, it will change. So you just click on the sample data, it will update in your data table. So now I did 10 fold. Say if I want to do 5 fold, I change 5 and click on sample data. This is for cross validation. When you are doing 10-fold validation or 5-fold validation, you decide how many groups you want to create and then you change this here, change this number here. This, if I want 5-fold, I write 5 and click on sample data, it will change the data set here. 150 into 5 groups, 4 groups will be for training and 1 group for testing. Yes. Yep. Not. This one comes from this. Double click this. It will. Okay, I'll do it again. I'm clearing everything and we'll do it again. Yeah. So I'm creating a new widget. I'm starting with the file. Now here I'm loading my data set, the whole data set, right? Right now I have the iris data set. Now this, if I create a data table, this will just show me what data it has. It has 150 data, right? 150 lines. Now I want to split this into a test set and a training set. For that, you use the widget called data sampler. Data sampler. Now data sampler, double click on that widget, it will give you this dialog box. Here you can choose what's the proportion you want on training and testing. Decide your way of splitting, decide how much you want to split to, and then just sample data, right? Data sampler will only sample the data, like it splits the data, but you can't see what it split it into, right? For that, you create new data table from the data sampler output, just to see what is the data here, right? You need one data table for training set, you need one data table for test set. Yes. So the first one is just training set. You don't have to change anything. You did a 70% sampling. So your 70% is there in your first data table. Remaining data, you just click in the two boxes, it will just click in one box and drag to the other box, it will go. Then okay. So your first data table had training data, remaining data, that 30%, it went to the test data set. So now you double click this just to see whether your training and testing split has happened properly or not. So you have 105 in one and 45 in the other. You want to change this ratio, go back to this place, change it, click on sample data, it will update it both the tables. Now once you split the data, then you proceed, like give this data into any ML model that you want to work with. So it will use the training data to work, learn, and use the remaining data to test. You can do the same for cross validation also. Instead of doing a simple test train split, you do a cross validation, decide how many groups you want to split the data into, type that number and then sample. So it will split the data into that many groups. And when you are implementing an ML algorithm, it will learn from, split the table is not coming. What do you mean split the table not coming? Okay, you go from data sampler to data table. Data sampler is the one that splits the data. Data table is one you view the data. You remove this second one. Come on. Yeah. Okay. Close this. You create a new data table, not with the same data table. You can remove that. You can remove that data table. You don't need that. Now sampler. Create a new data table. You get click and drag. Okay. Now connect the two. Now double click on this. Oh, you didn't load a data set. Your file is showing into, right? Then it will show here. Yeah. So if you want to, like it says how many fold that you want to keep and how many you want to train. I showed 1 to keep, 4 to train. You can do 2 to keep and 3 to train. That doesn't have to change, right? Splitting is not going to change. It's just how many to keep and how many to use. Yeah, when you add a new algorithm, like in any ML algorithm, after the sampler, you do test and score, and then you put a algorithm separately, and then connect the algorithm to test and score from the test and score. It's almost. Huh. You're clarifying. Okay. Okay, so everyone is able to do this? Yes. So once you split the data, you add any ML algorithm, you do the testing and scoring for that algorithm. It will show you what's the training error and the testing. So you don't need this. Do a test and score. Okay, in test and score, you do a cross validation. Okay, when you're doing test and score, you have to give two inputs. One will be for the training data, the other will be for the test data. So you have to give both separately. So two inputs, and the second one should be remaining data as test data. Now this gives you the scores for training and testing. So you test on training data, it gives an accuracy, training test data. Okay, so you split the data sampler. Now you want to implement an ML algorithm, add an algorithm, and then you combine them with the test and score. Right? And for test and score, if you have a test data, then you have to send two inputs. One will be your training data, another one will be the test data. So you double click on the link and it will show you what links you have. So data sample to data will be your training, and remaining data to test data will be your test set. Now here you do this test on test data. That will give you accuracy for the test data. Yes. Yes, you're all okay with this? It seems you have some assignments and you're supposed to work on that, so if you are okay with what I've shown, then let's wrap it up. Thank you.